Are supersonic planes about to make a comeback? Can lasers burn a hole through the Earth's crust?
Whoa! It just started to fly apart.
And why do robotaxis keep making dangerous mistakes? I've spent the past year asking tough questions about why the future we were promised hasn't arrived yet. Here are 6 futuristic things that are almost impossible.
Have you ever looked up at a skyscraper and said, how tall can this really go? Well, I'm about to climb up there to show you something.
Until 1971, this was the tallest building in the world. After that, for decades, buildings got taller and taller until the Burj Khalifa was built in Dubai. That's now the world's tallest, and it's twice as tall as the Empire State Building. And soon, a tower will open in Jeddah, Saudi Arabia, that's 3 times as tall.
Frank Lloyd Wright said a mile-high tower is technically possible, and he designed one back in the 1950s. I spoke with the people behind the tallest towers ever, and they told me exactly how far we can push it.
I think Jeddah Tower is the next step. I don't think that it's the limit of how tall we can go. The sky's the limit.
We went into the hidden parts of the world's super talls.
I wanted to show you guys what it feels like to be at the top of the world.
To answer the question, how tall can we actually build? Who pays for it? And is it even worth it to keep building higher and higher?
And what did we find out? The higher the build, the stranger things get.
So the first thing you need to know is that there's not one single right way to build a skyscraper. From the steel frame inside of the Empire State Building to the more modern outrigger system that's inside One World Trade.
We look at these structural systems we create for tall buildings as like different species, different animals, that work at different scales. But unlike nature, we don't need to evolve from one to another. We can create completely new systems. It's not really derivative from something before or evolving for something before.
Up until the Burj, all of these buildings had something in common, a single tall support. You could add what's called outriggers, which were mechanisms to connect the outer walls to that central concrete structure. But there's one way that you can add support to a super tall that's very simple. The breakthrough of the Burj Khalifa was this 3-part design that unlocked a new era of super tall structures.
We created this new species, this new system, and then we gave it a name. We called it the buttressed core.
This buttressed core allowed the Burj Khalifa to dwarf everything before it. It's 828 meters tall, and while the record for the world's tallest building is usually beat by incremental jumps, the Burj Khalifa was over 60% taller than anything else built before it, and nothing completed since has even come close.
The tripod form is extremely efficient. So think of it as a 3-legged stool. When you have 4 on a stool, if one's kind of a little off, you kind of feel it rock, but 3 is very efficient.
The wing-like design also reduces the need for materials that were used to build earlier skyscrapers.
There's actually more steel inside the Empire State Building than there is in the Burj Khalifa.
So what's it actually like to go up the world's tallest building? Well, we sent a producer there to find out.
Thanks, Dan. I'm going to show you the full experience of at the very top of the Burj Khalifa. It's humongous, it's gigantic, and it's surrounded by all kinds of tall skyscrapers, but it exactly dominates them. I can't even capture it in a horizontal format in the widest of the lenses. You can see that.
The first thing to note is that the experience of going to the top of the Burj begins long before you even reach the building. You have to walk through the massive Dubai Mall just to get to where the line starts. It turns out that going to the top of the Burj demands endurance. The total cost of a trip like this with the VIP ticket, getting there, and souvenirs would probably run about $500.
I'm embracing this view. This is what human admiration and vision can lead to. I can see the infinity from here.
Our producer may have enjoyed his trip, but it got me wondering, are these incredible feats of human engineering just expensive tourist traps? Well, look at the numbers. The Burj could be raking in as much as $700 million a year from over 9 million visitors. That's twice the amount tourists spend to visit the Empire State Building and Eiffel Tower combined. One way to think about it is that the Burj made back its $1.5 billion construction costs in just 3 years of tourism revenue. It could be worth it to build tall just to stick a gift shop on top. The buttressed core has gotten us higher than ever before, and a similar design is being used in the Kingdom Tower in Jeddah, Saudi Arabia. However, it might not be the right form for a mile-high skyscraper.
I think there's a limit to how high this structural system is appropriate. Is it, certainly a kilometer, maybe 1.2 kilometers. At a certain point, you have to create a new species, a new animal. A new structural system can go that high.
That's exactly what Bill's team did. Later, you'll see their design for a structure 10 times the Eiffel Tower that overcomes all of the limits of height but looks nothing like the Burj or the Kingdom Tower. But first, let's look at why the Burj itself broke with symmetry and why that lopsided look is one key to going higher.
Tell me, where are we at, Bill? What's going on here?
Okay, I'm here with Brad Young, who runs the wind tunnel here at the SOM. Brad and company spent like months and months calibrating this wind tunnel so that it accurately represents the velocity profile of wind that you see in the real world. What we use here is good German, very expensive styrofoam, okay? Because the model needs to be very stiff, but very lightweight. Okay, so Brad's firing up the wind tunnel. You'll see that there's a series of 6 fans at the end of the tunnel. All right, here it is. It's starting to fire up. And what the wind tunnel does, it shapes the wind profile that matches what you see in nature.
The secret to this carefully calibrated wind tunnel? Lego bricks. They're used to simulate how trees and buildings can affect airflow.
So we use computational fluid dynamics. That gives us a little bit of a better graphical understanding of what's happening and allows us to understand, why some of the changes we're making to the building may have the effect that we measure but we can't see. So this is a computational simulation of what you're seeing in the tunnel.
That computation is showing one of the key things that makes building super tall so difficult. They're called vortices.
So imagine you have a kind of a round shape and the wind is blowing towards you. On the other side of the building, there's kind of this vacuum that happens, and then as the wind vortexes come through each side alternately, they create kind of like a mini tornado that pulls on the building, and that can be really dangerous, especially if the building starts to move at its own frequency.
And this frequency is the key thing to watch for. If the timing of this wind syncs up wrong, this force can multiply. You see this most often with bridges. The Tacoma Narrows Bridge, known as Galloping Gertie, had a resonance that almost exactly matched the wind speed, causing it to bend and twist in the wind until eventually it collapsed. So there's one key focus for super tall buildings: confuse the wind.
As the wind hits the body of the building and organizes the vortices on either side, it can begin to rack the building from side to side, and so we want to disturb that. And so we're confusing the wind at every chance we get. The wind design is the governing factor on the super tall.
But there are a lot of different approaches to that.
Now, often what we're doing is using texture or form to confuse the wind to alleviate that behavior. But sometimes we actually accept the wind. And we've done projects where we've actually brought the wind through the body of the building, for example, or utilize spaces to ventilate the building, just like you would in a jet or in a high-performance car.
Right here, 432 Park, you can see that there's empty floors on it. They're called jump floors, and they're meant to let the wind pass through to cut down on the shear forces on the building, but there's actually nothing on those floors. It's just empty. And it also makes the upper floors even more expensive because they're even higher up.
But despite the intricate work that goes into the structural engineering of a super tall building, not everything can get worked out in a computer program.
It's quite surprising, but minor changes in the shape of the building can make dramatic changes in the forces in the building.
The Burj Khalifa was essentially reversed completely after wind tunnel testing. The spiral originally went up clockwise, but was changed to counterclockwise because of these real-life results.
And the data we got back was not good, okay? The forces were too large, the motions were too large. And so it's kind of a little bit ironic that if the first shape and structural system had worked well, we might have stopped there. But because it didn't, we had to make enough changes that we could then actually go much higher. And the building changed in height by 300 meters. It's 300 meters taller than when we started, which is essentially the height of the Eiffel Tower.
And there's one more trick that more modern skyscrapers have to survive the wind that's actually inside the building.
Did we do that?
Oh, it wasn't on, so okay.
Okay. We're going up a staircase from the summit where tourists are allowed to go. There's extra steps up. Ed, what floor is this technically?
That's 93, this is 94.
94
93 to 94.
Got it.
At the top of some of these buildings are hidden monoliths, super heavy objects tuned precisely like a musical instrument.
It's called a tuned mass damper, and it basically acts like a super heavy pendulum that offsets the wind forces on the building and makes it so that the people who are at the upper floors don't feel that sway at the top. Every tuned mass damper is different because it's calculated to the size and structure of the building. In Taipei, the Taipei Tower has a beautiful sphere that's sort of a sculptural element that visitors to the building can go look at. In Shanghai, the tuned mass damper uses electromagnets to modify how it works. All right, so now we're gonna go inside to see the TMD at the top of One Vanderbilt, which is the 4th tallest building in New York City. Let's go.
Do you remember how much it weighs?
Yeah, it's 500 tons.
Wow.
About 1 million pounds.
When you're doing the calculations for putting like something like this in a building, what are the factors that you have to account for to make sure that you're getting this the right size and positioning?
The classic example is the wine glass. If you take a good crystal wine glass and you flick it, you could hear it, right?
Right. It has a certain pitch to it.
It's just like that wine glass, every building has a resonant frequency.
Right.
Which we can calculate. We're designed for a 110 mile an hour wind.
Wow.
And a hurricane actually hitting Manhattan.
Right, like a direct hit hurricane.
A direct hit hurricane. Yeah, I don't think that building twice as tall as this is going to be an issue in the next 10 years.
You heard it here first.
Assuming somebody wants to pay for it and actually has a use for a building that tall.
But here's the thing about TMDs. The Burj Khalifa doesn't have one. That's because it has a buttress core design, it has concrete at higher floors, and the way it's designed to confuse the wind, it doesn't really need one. If we're gonna build a mile-high skyscraper, we're probably gonna need a TMD, or maybe more than one depending on how high up it goes.
Let's be clear, all these measures have less to do with preventing the worst case scenario of a building collapse, and a lot more to do with the comfort of people who are going to be living and working at the highest floors. And as you could see, mitigating those factors can get very, very expensive. But what if no one needs to go that high up in a building?
One of the cheat codes to adding height onto a building is to add a spire. Just look at the Chrysler building. The architects of that built a spire inside secretly as it was in competition with other skyscrapers at the time to become the tallest. And in the last months of construction, they shot the spire up and got the world record. That was until the Empire State Building was built. But a spire is an easy way to add height onto a building. And on the Burj, the spire is actually 244 meters tall, which means that 30% of the structure is not meant for regular visitors at all. The only people that are allowed to go up there are technicians who have to change a battery on this specific device that attracts lightning bolts, and a few lucky celebrities. That means the spire on the Burj Khalifa alone would be the 11th tallest building in Europe. But if we're only trying to go as tall as possible, why not just build one giant uninhabited spire? If you broaden the definition of the world's tallest building to the world's tallest human-made structure, things start to look a lot different. 45 out of the top 50 tallest structures of all time are not buildings at all. And to show you what I'm talking about, we're going on a little road trip. We're about 15 or 20 minutes outside Hartford, Connecticut right now, and we are approaching our final destination. Oh, wow, I can see it now. That's why we're here. The
The tower that we're going to see, the WTIC or WHPX, which is the later call sign for the tower, is over 400 meters tall. That makes it taller than the Empire State Building, but it's not even close to being one of the tallest masts in the world. The tallest radio tower was actually the Warsaw radio mast, which was built in Poland in 1974. And the signal from the mast could be heard as far away as the US and Canada. But here's the thing about these towers. They're built for maximum height with the smallest footprint possible. And when you're talking about a steel tower that just goes straight up and down, well, you need something to tie it down. This is the anchor for a guy line that you can see goes from there all the way up to the tower. And each of these lines is kind of like a finger trap. The more you pull on it, the tighter it gets. But if one of them fails, it could be catastrophic. In 1991, during much needed maintenance on the Warsaw Tower, the main guy line got disconnected and a gust of wind came and twisted the structure and the entire thing collapsed. The tallest structure in the world had collapsed and miraculously no one was hurt, but it wasn't a one-off. Made it to the top. There's a few guys working. I'm making a video about like tall structures, so I'm just taking a video of the tower. I'm just gonna take one quick shot just to show the bottom, because I think a lot of people don't realize that these things end in a sort of a, it looks like really unstable, right? Okay, so we found out where we're not allowed to get this close, but there's a facility here and there's guy lines in every direction holding this thing up. There have been at least 9 collapses of towers like this over 600 meters. And that's because the guy lines and the way it's set up are so fragile that if you lose the support of one of them, the tension in one of them, the thing will twist and come crashing to the ground. Antennas like these almost always top out at around 2,000 feet. And that's because any higher than that, and they start to pose a risk to aircraft, particularly small aircraft. But there's no reason that you couldn't build something like this to surpass the Burj Khalifa, and for a fraction of the cost and material. Something like this is super cheap. It cost about $500,000 and only took 30 days to build some of the tallest masts of all time. Now, do you remember at the beginning of the video when I mentioned the super tall structure that was designed by the engineer behind the Burj Khalifa? Well, Bill Baker thinks an uninhabited structure that goes straight up and down could easily hit 3,000 meters, which is well above our 1 mile limit.
The Eiffel Tower was originally called the 300-meter tower. If you look at the drawings, that's what it says, in French, of course. And so we thought, well, okay, that was, 1889. Here we are in the 21st century. How about let's go 10 times as high, 3,000 meters, okay?
That's way over 1 mile high. In fact, it's almost 2 miles. If you put that next to the Burj, you can see how tall it really is.
It behaves very well in the wind, both because of the shape and also because of the porosity. As it goes up, eventually it becomes so dense that we have to make it sparse again and stop some of the pattern, and then it gets sparse again and eventually becomes solid at the very tip.
Structures like these work well against the wind because it's essentially hollow. The wind just kind of passes through, adding glass and floors and concrete and places for people to live, and the whole thing stops working. Man, Prakar got to go up to the top of the Burj Khalifa, and I had to climb up Rattlesnake Mountain to go look at a broadcast tower. That's not fair. That's not fair.
Bill's reboot of the Eiffel Tower looks more like a broadcast mast than it does like a functional skyscraper. There are no apartments, there are no offices. It's actually designed to be a vertical farm and tourist attraction. That made me wonder, how do we define what a building actually is? Couldn't we have a few people living on the lower floors and just stick an antenna on top?
Oh, you've stepped on the third rail, my friend.
That's Daniel Safarik from the Council on Tall Buildings and Urban Habitat. They're the ones who make the rules on how to measure the world's tallest buildings.
So the short answer is no, we don't count the antenna in the ultimate ranking height of the building. We have 3 different types of criteria. There's height to tip, which is the absolute tallest thing on the building at any point in time. The problem with using that as your ultimate height determinant is that it often changes. So it's very likely to be replaced or superseded by a different kind of technology several times over the lifetime of that building.
Take Chicago's Sears Tower, now called the Willis Tower, and Kuala Lumpur's Petronas Towers. Even though the Petronas pair took the title of the world's tallest in 1998, the very tip of the Sears Tower actually stands almost 100 meters higher.
The things on top of the Sears/Willis Tower are antennae, and they have been different heights, significantly different heights over the years. Whereas the spires, permanent architecturally designed fixtures on the top of the Petronas Towers and others like it, have stayed the same. The so-called architectural height, which is the second criteria, outstrips the other two. The third one is, of course, the highest occupied floor.
And according to the council, to be considered a building, people must be able to occupy at least half the floors. So for our mile-high structure to actually be counted as a building, we could have 800 meters of habitable space, followed by almost 800 meters of spire alone. So let's recap. We know we're going to need a new structural system, rigorous wind testing, maybe a tuned mass damper at the top, and almost 50% of the building can be a spire. But what would something like this actually be made of? Once you've designed a mile-high building, the actual work has only just started, and the first step is a strong foundation. It's not just about digging deeper, but finding the right location.
What's interesting about tall buildings is that a lot of times they're building, in cities, okay? And where are the cities? A lot of times they're in river valleys, where there's ports, and a lot of times they're places where there's really terrible soil. and so that's not unusual.
The record for the deepest foundations for a skyscraper goes to the Petronas Towers in Malaysia. The building site actually had to be moved about 60 meters to make sure it was sitting on the right kind of rock. 104 concrete piles supporting it stretch up to 114 meters, or 374 feet deep. That means 25% of the structure's height is buried deep underground. The strength of concrete has been a big limiting factor for building high, but materials have come a long way. Concrete especially has changed dramatically since the 1950s.
It's almost 10, 20, 30 times stronger than then. And why is that? There's been a lot of innovation in the material. One such innovation is called a superplasticizer that helps reduce the amount of water that goes into concrete. So now we're talking about ultra high performance concrete that can really support, theoretically support a mile if it's thick enough.
And these concrete developments were crucial when building the Burj.
So one of the innovations was an extremely high pressure pump. And so it can pump it really high up. And it's pretty important that this is done very quickly because, concrete cures.
Due to the heat of the desert, this concrete could only be pumped at night too, and it had to be filled with chips of ice to stop it setting too fast.
Pretty interesting to realize that, all these small niche things are actually really what is making these things possible.
And what feel like niche problems are going to be the real sticking point when building super tall. Building a mile-high skyscraper in the heat of the Middle East will have entirely different challenges to doing the same in cooler climates. Every expert I talked to said that we can build taller, but each time there's going to be more and more crucial considerations and less room for error. Just take the kilometer-high Jeddah Tower currently under construction.
So the logistics or strategy around getting that concrete up to over a kilometer is part of the design challenge. That needs to be extremely well coordinated because you're not going to go back in and alter the concrete during construction to solve your problem. We often kind of embed in our guys that, on these projects, when you make an error, you can multiply that error by 1,000 times across the scale of this building.
It's extremely expensive to retrofit a building once it's already up. Look at the Empire State Building. The owner spent $1 billion modernizing it over the last few decades. What most people don't know is that skyscrapers are only designed to last about a century.
The average age of the 200-meter building that, when it is being considered for demolition, according to our research, is around 41 years, which is pretty pathetic.
What happens to buildings like the Burj Khalifa 100 years from now when they get too costly to maintain? Is it simply left to crumble or pulled down at a much larger expense? That's why Gil's firm made sure to use the best-in-class vendors for everything on their upcoming project.
When we first started this project, we went out and interviewed the best elevator consultants in the world, the top 5. We did top 5 mechanical engineers in the world, the top 5 plumbing engineers in the world, structural engineers, because we knew we were on a path of doing something that hadn't been done before. And so we learned a lot about the systems. Now remember, over 14 years, you can imagine that those things change.
Those elevator consultants he mentioned, they're especially important. It seems like the structural issues might be the biggest limiter for a super tall, but it's actually elevator technology that still needs to catch up.
If you're in an 800-meter tall skyscraper, no one is going to want to take the stairs. So that's why elevators are probably the most important technology inside of a super tall. In a 500-meter elevator shaft, there could be something like 27,000 kilograms of steel rope. And the reason there's a limit of 500 meters for an elevator is because after that point, the elevator can't support the weight of the rope anymore.
The solution so far to this 500-meter limit is to have multiple elevators and sky lobbies where passengers can change between them. But this takes up a huge amount of space. And if there was a mile-high building, changing elevators twice or more to get to your apartment is going to be frustrating for anybody living at the top. This 500-meter limit looks like it's been broken by something called ultra rope. It's an elevator rope made from carbon fiber, and it'll be used in the Jeddah Tower. This would allow elevators to go up to 1 kilometer high, but if we want to reach even higher than that, we'll need newer technologies again. Frank Lloyd Wright was actually one of the first to consider a mile-high building when he drew up the Illinois, a 528-story tower with parking for 100 helicopters. He was using a tripod-like design way before anyone else had considered it, but the most outlandish part of his design was actually the elevators. The plan was to have 76 5-story high elevators that could travel 1 mile per minute and be atomic powered. These would be mounted on rails, kind of like vertical trains. And here's the thing, once the elevator challenge gets solved, designs can veer into the fantastical.
If we are beginning to, fly cars or vehicles or drones into the building, if we're beginning to advance technologies for elevatoring that can move sideways or can run on rails, the sky's the limit.
Imagined in the 1990s, the Exceed 4000 is a 4-kilometer tall behemoth that would loom over Tokyo's Mount Fuji and be able to house 1 million people. But even the director of the firm behind it said it wasn't meant to ever be built. The tallest structure ever proposed by architects is the Tokyo Tower of Babel. It looks similar to Exceed, but it more than doubles the height to 10 kilometers. It was designed to house nearly the entire population of the city of Tokyo.
You could go probably 9,000 meters, height of a mountain, like the Mount Everest. At some point, it'll just take so long to build you won't ever get there, and so you may never get completed. The limit is going to be set by time as much as any time and political will, and financial resources.
The Tower of Babel would cost 3 quadrillion yen, or $22 trillion. That's 14,500 Burj Khalifas, so basically a made-up amount of money. And yes, you may have seen photos of an elevator to space or an orbital ring that surrounds the entire planet. Structures so high they push out of the atmosphere. Those might be impossible, but the reasons why are the subject for a completely different video. So more than wind, materials, and technology, it turns out that the real limit will always boil down to the bottom line. The top 3 tallest buildings in the world cost an average of $2.6 million per vertical meter. There are so many reasons not to build tall, and developers can make money just building regular height buildings. But these projects are about so much more than economics. They're about putting your city on the world stage.
The purpose of a tall building is interesting. I think a good example is the Eiffel Tower. It's not really a building, it's a restaurant, it's an observation tower. But it's a placemaker. It tells you we're here. You can't imagine Paris today without the Eiffel Tower, or France, or Europe, or the world. If you're in a country or a city which has a lot of ambition and you're highly optimistic, a distinctive, good, tall building is one way to do it, to kind of plant your flag,
When I first started this story, I have to admit, I was skeptical that buildings could get much taller. But now that I've talked to the people building them, the question of a mile-high tower isn't if, it's a matter of when. And I guess the question is, how much would you be willing to pay to buy a ticket to go to the top? The last time anybody besides a fighter pilot was able to hit Mach speed was in one of these. But that was 20 years ago. The Concorde didn't just hit Mach speed, it went double the speed of sound, flying from New York to London in under 3 hours. Today, you can only go visit a Concorde in a handful of museums. It's a relic, left behind by an industry that invested in efficiency rather than speed. But look online, and you'll see that there's a huge appetite for supersonic travel. The race to supersonic is heating up. I've talked to nearly all the companies building these new planes, and I asked them, why is it so hard to bring back supersonic? And what's the limit to how fast a passenger plane can actually go? In order to understand the challenges that they're up against, I decided to start here at the Concorde. So my first impression of the plane is that the head clearance walking in is extremely low. I'm 6'4", and I have to really uncomfortably duck down just to get in this doorway. So we're gonna see what it's like inside, but it's obvious that this plane's dimensions are totally different from normal commercial airlines. First of all, the head clearance in here, thank God, is a little bit better. But I am about touch. If I stand up straight, my head is touching here. So it is pretty narrow and low. Here's my hand against the window. Look at how small it is. When this plane was flying at such a high altitude, if there was a failure of one of the windows, these small windows were meant to slow that cabin depressurization. So it was a safety measure. And actually, on some of the newer planes that we're talking about, they don't even have windows. Attention Concorde passengers, on today's menu, duck l'orange, caviar, and champagne. Lots of champagne. I always wanted to hold one of these. Anyway, one of the things about the Concorde, it wasn't just about speed, it was about luxury. Every seat on this plane was considered first class, and the service was first class. There was a culture created on this plane of frequent flyers. A lot of the time celebrities were getting invited to the front, to the cockpit, and the pilots that we talked to have some really fond memories of meeting those people, interacting with them, and almost creating friendships with them.
The rock stars of that era, the Rolling Stones, the Beatles, they would use it quite a lot, and they'd certainly be there, and I certainly remember them. And I had a menu where I was collecting my favorite rock stars' signatures. I sent it back to, I won't mention the name, sent it back to somebody for that person to sign, and they thought it was a gift for them as it was their birthday, and they walked off with it, which was a bit of a blow, to put it mildly.
This is the forwardmost cabin before we get to the front of the plane and the cockpit, and I'm comfortably standing up now, finally. So that might be explained by the fact that, as you can see, the body of the plane gets sort of narrower towards the back. So we're in the front of the plane, we're towards the cockpit. The view is extremely narrow. If this was a car, I would not feel comfortable driving this on the road because the visibility down to the ground is extremely poor, hence the droop snout design. So the Concorde's droop snoot was a feature that allowed pilots to see the runway during takeoff and landing, but then snap back into place when it was hitting supersonic speeds over the Atlantic Ocean. The beginning of the end for Concorde came in 2000. After about 30 years of service, tragedy struck. So we're underneath the plane now, and you can see the landing gear on each side. And one of the things that's understood about when the plane actually did crash is that there was one of the tires hit something on the runway, and it kicked up
the piece of debris into the jet fuel tanks, which are right here. And that's what caused the fire that caused the eventual crash.
Concorde did start flying again not long after, but its fate seemed sealed. And the last flight was a few years later on the 26th of November, 2003. So over 20 years later, have any of these companies solved the big problems that Concorde faced while it was flying? Probably the most challenging obstacle these planes will have to overcome is their noise. The sound of a sonic boom has remained the biggest obstacle to supersonic flight since the very beginning.
So far, 7,000 people have complained to the Ministry of Technology and to the Noise Abatement Society. Only one man seems to have come out in direct praise of the boom, and that's a 74-year-old old-age pensioner who claims that the boom has cured him of his deafness.
We got a purpose to stop the Concorde.
In 1973, following a public outcry, the US banned overland flights for supersonic jets, followed by most other countries. That's why the Concorde was only ever allowed to fly supersonic over water. Planes have been getting quieter over the past 50 years too. That's thanks to improvements in aircraft design and more stringent government regulations on sound. So, a loudly booming supersonic jet would be even more noticeable compared to modern subsonic travel. So how does a sonic boom actually work? Here's what happens when anything travels faster than the speed of sound. So, sound is a wave of pressure, and for a stationary object, it travels in concentric circles out from where the object is. The waves of sound get pressed up against each other, and that wall of high pressure, that is the sound barrier. Breaking that barrier means an object is traveling faster than the sound it makes. It leaves behind a loud shockwave, kind of like the wake behind a boat that's going really fast. And that is what you call a sonic boom. If a plane booms too close to the ground, it can actually shatter glass. Many people, including myself before making this video, thought that a plane booms one time when it breaks the sound barrier, and then it's quiet as it's moving through the air. That's actually not what happens. As long as a plane is traveling faster than the speed of sound, it's leaving that sonic boom sound behind. For every 1,000 feet of altitude, the boom carpet left behind the plane is about a mile wide. So a plane traveling past Mach speed at 60,000 feet has a 60-mile wide swath of land underneath it that's hearing that boom boom sound wherever it goes. And for those on the ground, that boom is about 105 decibels. That's at least twice as loud as a normal plane flying overhead, and it's equivalent to standing next to a chainsaw or a car horn. So let's look at our 4 planes. It's worth noting that I originally spoke to 5 key players, but one of them went under while we were making this video. And it just goes to show you how much of a challenge developing these planes can be. Each of them has completely different approaches to supersonic travel, and each faces different challenges. The X-59, Boom, and Concorde all use similar technologies, flying at 60,000 feet and hitting between Mach 1.4 and Mach 2. Those kind of speeds can get you from New York to London in 3 hours, rather than the usual 7. The Halcyon will use a ramjet engine along the turbofan to get it all the way up to Mach 5. That would get you from New York to London in just an hour and a half. And the Stargazer is using a detonation rocket engine, something you don't commonly see outside of missiles. That might just do the same trip from New York to London in under 1 hour. So how are these 4 planes going to tackle the noise issue? Boom's Overture isn't looking to reduce the sonic boom at all at Mach 1.7.
With Overture 1, we're starting really simple. We're putting sonic booms out over open ocean where no one's there to hear them.
US regulations still ban all commercial planes from going supersonic over land. But researchers at MIT found that 78% of demand for supersonic transport was over land routes. Almost 40% of that was on US domestic flights. If these regulations change, Boom says the Overture could achieve a boomless cruise, flying at just over the speed of sound over land without an audible sonic boom. But this phenomenon requires specific atmospheric conditions to achieve. Flying any faster than that without making a lot of noise requires some really innovative design, and that's where the X-59 comes in. The X-59 isn't aiming for commercial supersonic flight like the others. It's actually one of 66 X planes developed by the US government. The X is for experimental. The first X plane was the Bell X-1, which was the first plane to break the sound barrier in 1947. The X-13 tested vertical takeoff and landing. The X-15 was the fastest piloted aircraft that never left Earth's atmosphere, and it hit Mach 6.7. It's taken NASA and Lockheed 6 years to build a prototype X-59. First off, X-59's engine is on the top, not underneath the wings.
So by putting the engine on top, we kind of shield that shock wave from reaching the ground.
Then there's the nose. It's a little hard to miss as it's 38 feet long.
The idea of minimizing the sonic boom is to keep those shock waves small, weak, and relatively evenly spaced. So that long nose essentially starts that process. It sets up those initial shock waves to be weak and kind of equally spaced along the first part of the airplane.
And lastly, the light carbon fiber further helps to reduce the plane's weight. Otherwise, the X-59 is built from parts of other planes. It's got a T-38 cockpit, which is a favorite for test pilots, and landing gear from an F-16. So, did NASA actually figure out how to quiet the boom?
We feel that we have. I mean, we have, shown in a wind tunnel, in an experiment and in experiment and analysis, that an airplane can be shaped so that instead of producing a boom, it produces a thump.
Their aim is to reduce the boom from 105 to 75 perceived decibels.
That's equivalent to either a car door closing across the street or the sound of distant thunder.
As part of the Quiet Supersonic mission, NASA has exposed communities to a simulated sonic thump. In 2018, they conducted one of these surveys in Galveston, Texas, with 500 civilian volunteers.
Mr. Windia, I heard nothing. That's Field Marshal. This is Foxtrot. Heard a faint thump.
Eventually, the actual X-59 will make about 60 flights over a variety of yet-to-be-named communities in the US to collect more data. But there's another much simpler way to reduce the sonic boom. Fly higher. Both the Stargazer and the Halcyon want to fly much faster and much higher than the other supersonic planes.
It turns out at roughly about 100,000 feet, a sonic boom about 100,000 feet is inaudible to the human ear. We can measure it with scientific instruments, but it's inaudible to the human.
That's Dr. Andrew Duggleby, the CTO and co-founder of Venus Aerospace. Just flying higher sounds like the easy solution, but when you're at those kind of altitudes, a whole host of other problems quickly appear. So right here on this chart, at 26,000 feet, is the death zone. That's where the air becomes too thin to breathe. It's why most climbers need oxygen to summit Everest. Almost all planes cruise higher than this, but the higher the altitude, the bigger the risk when something goes wrong.
When you're flying at 100,000 feet, if you lose cabin pressure and you don't manage it appropriately quickly, your blood will boil.
Oh my God.
So you basically have to treat it like a spacecraft cabin.
Yes. Airtight.
Yeah, but I think the solution that you see at the end of the day will look much more like a hybrid between a spacecraft cabin and an aircraft cabin today than just a pure aircraft cabin.
For high-altitude military planes like the SR-71, the pilots actually had to wear sort of a modified spacesuit because of the danger of the altitude and speed that they were flying. Our CEO is going to want to spacesuit up to get to their meeting in Tokyo a little earlier. I'm not so sure about that. But to be in a plane like this, there are so many things that could go wrong at a high altitude that you really need to protect your body from a worst-case scenario. And it's not just the pressure at high altitudes. There's one more problem with flying that high and that fast. The heat that could be experienced on the outside of this plane could sometimes top 250 degrees Fahrenheit, combined with the fact that the exterior temperature was well below zero at the high altitude, -75. That heat and cold caused a lot of stress on the outside of the plane. It meant that it needed a lot of maintenance, and it meant that it was a limit to how fast this plane could go. Going faster than Mach 2, Mach 3, Mach 4, Mach 5, you need to get into exotic materials. Aluminum, like this plane is made out of, just doesn't cut it anymore. It's when you get really fast that heat becomes the biggest problem. Aerodynamic heating increases non-linearly with speed. That means that as speed increases, the temperature rise becomes more dramatic.
What hypersonic really meant was the speed at which, and pardon my French, it's the speed at which heat kicks your ass. Like it's where heat becomes the defining problem. If you're trying to go make a missile, sure, maybe you want to go hypersonic because you have other reasons to go really, really fast to avoid defenses, right? There might be like military reasons to go crazy, blazing, fast, hot. But I bet if I look at this from I want to sell commercial flights, how do I keep the cost down and competitive? I bet I don't want to fly a Mach 5.
So one of the centerpieces of this museum is obviously the SR-71 Blackbird. You can see on the tail fin here, there's the symbol of Skunk Works, which are the people from Lockheed Martin, their sort of top secret division that works on stuff like this. This plane broke speed records going over Mach 3. It's one of the fastest aircraft of all time, and everything about it is built for high speed and to deal with heat. The SR-71 actually reached 600 degrees at Mach 3.2, and the glass in the cockpit here was actually 1.25 inches thick quartz material. If you were to touch that even with gloves on, you would burn your hand. So underneath the plane, the tires, again, because of the heat and the speed that it was traveling, these tires actually have inside of them nitrogen, not oxygen. The oxygen would just blow up at the speeds that this was going and the temperature it was hitting. And they also have a silver look to them because they contain aluminum, again, to deal with high heat that the plane was experiencing. The only way the fuselage could survive these temperatures was to make the entire thing out of titanium alloy, which is 10 times more expensive than aluminum. It's important to note that things that go into space and re-enter hit Mach speeds that are a completely different class. This thing would re-enter the atmosphere somewhere between Mach 16 and Mach 20. And that's why we always see on the space shuttles this black heat shielding on the front that's actually reinforced carbon. As it's re-entering the atmosphere, it's exposed to heat that's on a different order of magnitude than anything that's flying, at 100,000 or even 180,000 feet.
But even though these hypersonic planes aren't going to be hitting space shuttle speeds, finding solutions to these problems is going to take time and money. The Overture has been in development for 10 years at this point, and Boom's test plane just broke the sound barrier in late January 2025.
There we are. XB-1 is supersonic, faster than the speed of sound.
The X-59 is expected to take its first flight in 2025 and has already cost $632 million. That sounds like a lot, but building a plane is never cheap. Both the Airbus A380 and Boeing 787 Dreamliner cost over $20 billion to develop, and that's with huge manufacturing arms already in place. The CEO of Boeing said if they were to develop a new plane today, it would cost $50 billion.
Exosonic was going to be the 5th plane on our list. They were also aiming for a very achievable sounding Mach 1.8 plane, using already existing engine technology.
They closed their doors completely in November 2024. I spoke with the CEO before they went under, and he was a little more realistic about timeframes for this technology.
So at least for the airliner, we don't see that coming into the market until like mid to late 2030s, which I think, UBS or some other bank had a similar conclusion.
The speed of developing these planes isn't helped by the fact that there's literally only one place you can fly supersonic planes over land in the United States, the Edwards Air Force Base.
We can take off and immediately climb up to 30,000 feet where we're now cleared to go supersonic, and that doesn't exist basically anywhere else in the country, and certainly probably not even around the world. Edwards Air Force Base was established around 2 dry lake beds. It's roughly 35-ish square miles of naturally dry, compacted surface that's hard enough to land airplanes on. So there are other areas, especially over the water, where you can be doing supersonic flight tests, but that's not exactly a place you want to be if something goes wrong during the flight test. I don't want to be over the water, and I certainly don't want to be far away from a landable surface.
But the area is not completely uninhabited. We asked a few people in nearby towns what a sonic boom sounds like.
I've heard it described as the sound of freedom.
Well, sometimes you get the rumbling, the building will shake. And other times it's just a loud, like MAD or something going off, a big explosion.
So when people come here and not from the area, they hear the noise and the first thing they want to do is run out the store because they think it's an earthquake. So to me, it's funny, and I just look at the reaction and then let them know it's a sonic boom.
So NASA,
Lockheed Martin, Boom, Hermeus, and other organizations building supersonic prototypes will at some point be testing in this one strip of land in California. And it's not just the test flights. Finding the space to test engines is even more of a challenge. But that's changing. And we went to Jacksonville, Florida to check out why. This is Cecil Airport. It's outside Jacksonville. We're here for a press event. So basically, Hermeus is opening up a new facility here that's called HEAT, and it's going to be for testing engines. And they've got their quarter horse prototype plane inside the hangar here, so we're going to get to check that out, which is pretty cool. Let's go take a look at this plane. Wow, this looks crazy. Look at this.
So in order to test the engines associated with hypersonic flight, there's only a couple places in the country that you can do it at the scale that we need, at the scale of the F-100. And that primarily, the kind of like go-to one is Arnold Engineering Development Complex. And that facility is bottlenecked in the entire country because everyone wants to get in there. And so what we want to do is not only bring in something that will help us accelerate our roadmap that isn't bottlenecked where everyone is trying to get there, but also increase the capability of the country.
So this is the tunnel. This is the inside of the tunnel where they're going to be testing things like the quarter horse and other engines. And it's hard to tell, but it's super, super quiet.
Hermeus, an Atlanta-based firm, is arguably the furthest along in testing their hypersonic prototypes. They're planning to modify the Pratt & Whitney F-100. That's the same engine that's inside an F-16. So what they're doing is cocooning that engine inside of proprietary technology to take what was an engine that could go Mach 2 and giving it the capability to go Mach 4, 5, and above.
You spend a lot of time in Washington.
I do.
And that means you're probably talking to people from the Department of Defense.
Yes. The systems you see the department investing in right now are one-way systems, right? You send them, they launch, and then they don't return. And so every time
AKA missiles.
Missiles, $20 million a shot or more. And so the cost is really challenging to scale. When you have a vehicle that returns, the cost per effect of those munitions significantly decreases. It would also have the impact of unlocking a lot of private capital.
Hypersonic weapons are at the center of an arms race among the world's superpowers. That's because a hypersonic missile remains within the Earth's atmosphere, unlike an ICBM, which goes up in a sort of parabola and then comes back down. In theory, it makes hypersonic missiles harder to detect. The US has spent over $10 billion on hypersonic weapons so far, about 3% of the overall R&D budget for defense, and it seems to be with good reason. China may have already tested a hypersonic nuclear weapon, and they've built wind tunnels that can test speeds up to Mach 30. According to articles we've read, Chinese scientists have patented an engine that can go up to Mach 16, and one Chinese company called Space Transportation is building what they call a rocket with wings. Take a look at this wild CGI video.
Do you think that the United States is behind on hypersonic?
I think it's an incredibly difficult competition. We have a different approach in general to how China and Russia have taken it. I mean, the flight tests kind of speak for themselves. The pace of flight testing that China, the CCP, have been able to demonstrate over the past decade exceeds ours by an order of magnitude. And I think that speaks for itself.
So I guess the last question is, when will you feel like hypersonic passenger planes are a real thing?
Ask me again once we've flown a hypersonic aircraft. That's step one that we gotta prove out.
So we know it's going to take a long time before supersonic or even hypersonic passenger planes are going to be in the air. And development is going to take a lot of investment. Another problem that Concorde just didn't have. The development of the Concorde was completely subsidized by the governments of France and the United Kingdom. Rolls-Royce, the engine manufacturer, was actually government-owned during the Concorde era because it had filed for bankruptcy. The airlines didn't even have to buy the planes.
I mean, initially, let's face it, the airplane was basically given to British Airways. I mean, they didn't have to pay a cent for it.
That level of state investment just isn't happening today, and that's definitely going to slow development.
I wouldn't be surprised if we saw a commercial supersonic around 2050. And to kind of unpack that, we would need to have both low boom aircraft and very abundant, very cheap SAFs in order for supersonics to succeed. And 2050 is about the time frame that I think it could happen.
That's Dan Rutherford. He's an environmental engineer that's been researching aviation emissions and policy for about 15 years. SAF stands for Sustainable Aviation Fuel. It's still an emerging technology, but it's one that's going to play a crucial role when it comes to these planes because of just how much fuel they need. Let's compare fuel use against standard subsonic airline travel. Commercial planes vary, but take the two most common planes flying today, the Boeing 737 and the Airbus A320. Now this of course varies on route, weight, and lots of other factors, but as a fairly high estimate, they both use around 3 tons of fuel per hour. Now compare that to the Concorde, which used a massive 22.6 tons per hour and for a lot fewer passengers. Even if you were to calculate it per distance, Concorde gets 13.48 miles per gallon to a 777's 80. Now, it's obvious that jet fuel is different from petrol. It's actually closer to diesel. But for a simple comparison, a full flight on Concorde is the emissions equivalent of every passenger on board driving from London to New York in a Ferrari 812 Competizione. And not only is it burning more fuel, but even the same amount of fuel use could be worse for the environment at higher altitudes too.
Because supersonics would fly very, very high in the sky, there's a concern that emissions from their engines will have a disproportionate impact, especially on the climate. And just kind of ballpark figure, if a plane is operating at, say, 33,000 feet, emissions from its engine stays in the atmosphere for like 2 or 3 days. But if you take it and you make it supersonic and you fly at 55,000 feet, what we call the residence time, or the amount of time the pollution stays in the atmosphere, is more like 2 or 3 years. And that's very concerning, both from climate change and then for ozone depletion.
How are these newer planes going to solve this efficiency problem? Well, the truth is they really aren't. The main problem is the faster you go, the less efficient travel becomes. In fact, Saudi Arabia wants to invest in supersonics precisely because of this. They highlighted the future of supersonic flight as a key focus in their oil sustainability program. Here's a graph showing the drop-off in efficiency at greater speeds. The higher up on the graph, the more efficient the plane. Boom is probably the closest of these projects to reality, and they claim that the Overture is 30% more fuel efficient than Concorde, maybe moving them up here. The Halcyon will be using a ramjet and end up somewhere around here on the graph, just beyond the SR-71. The Stargazer uses a similar engine, but also adds their brand new rotating detonation rocket engine for higher speeds. Rockets are way more inefficient, and if you look at the bottom of the chart, that's where you're going to see the rocket propulsion. Not a lot of planes use rocket propulsion for that reason. Compared to the Concorde's 22 tons of fuel per hour, this thing burned 20 tons of fuel per second. Now, it's not an exact comparison, obviously, because the planes that we're talking about are not launching directly up to get out of Earth's gravity well, but it just gives you an idea of how much fuel it takes to move weight, up into the atmosphere. I mean, you could kind of see the design is different, right? They're more compact. It's just about throwing as much power through it as you can. Venus is targeting a specific impulse of 1,250 seconds, which the company claims will put its hybrid rocket ramjet engine in line with standard ramjet performance. But that's still 80% less efficient than a 747. And rather than 400 passengers, it carries only 12. Engine efficiency may not be the sexiest topic, but all of these planes will undoubtedly be worse for the environment than subsonic travel we have now. It's not just the environmental impacts either. This fuel costs a lot of money, and it might just be the make or break reason that flying supersonic just isn't profitable for these companies.
It's a lovely goal. Everyone wants to go higher, faster, farther. We don't like to use that phrase too much, but but at some point there are limits. And in the case of airplanes, the limit for speed is Mach 1, a little bit below it, practically speaking, to be commercially viable. Beyond that, no.
Here's a graph of jet fuel prices over the last 50 years. This flat period of low prices was Concorde's era. Since then, fuel prices have shot up. So while a trip on the Concorde in 1999 costs about $154 per passenger in fuel, that flight today would cost over $700. And for Boom, the numbers are looking much worse. They've made a commitment to sustainable jet fuel.
Today's airplanes are actually only 50-50 compatible with sustainable aviation fuel. And Overture, we're designing to run on up to 100% sustainable fuel.
Sustainable jet fuel is a type of jet fuel made from either renewable sources like plants or algae, or repurposed waste that's intended to have a lower carbon footprint.
But the thing to know is that SAFs remain very expensive and very rare. So typically, SAF costs between 2 and 5 times as much as fossil jet fuel, and it only accounts for 0.2% of fuel use today. So it's very much a nascent technology.
So if Boom achieves their 25% more efficient than Concorde claims, and SAF costs the $8 per gallon that it cost recently, that means the fuel alone for each passenger on a flight from London to New York would be around $1,500. If SAF hits the highs of $10 that it did multiple times last year, that would be almost $2,000 in fuel costs for every single passenger. Those are really rough estimates, and maybe Boom will manage to squeeze a little more efficiency out of their planes, but it gives you an idea of just how expensive these fuel costs could be. We reached out to Boom about this, and they told us they're aiming for a $5,000 round-trip ticket. If that's true, $3,000 to $4,000 of that would be fuel alone. They told us, we've designed Overture to be profitable for airlines at fares similar to first and business class. That includes fuel costs, which we expect to go down over time as the supply of SAF increases along with demand. And there's one other big problem with this plan. SAF often isn't actually as sustainable as it sounds.
Well, there's a lot of diversity hiding under that term, sustainable aviation fuels. A SAF can be produced in a sustainable way with a good feedstock and reduce emissions by 80% or more compared to fossil jet fuel, but it also can be produced in a way that actually makes it more polluting than fossil jet fuel. So to take an example, if you take palm oil that's derived from like a deforested area and turn that into a SAF, then that's actually going to have higher life cycle emissions than fossil jet fuel, just because of all of the carbon you released when you cut down the forest. The US government is aiming for 3 billion gallons of SAF supply in 2030, which is a 100-fold or more increase from today. So those would be SAFs produced from corn or soy that offer modest, if any, greenhouse gas benefits.
It's going to be a tough task to balance out fuel costs, environmental damage, and heat problems, all while making a comfortable and affordable ride for passengers. Now that we've seen all the supersonic prototypes, who's actually going to fly on these things? All the CEOs we talked to said similar things.
I think it's typically the business traveler, folks that you would see flying in business class or first class today.
When we talk to people who are the most frequent international travelers in business class and first class, 97% of them say they want supersonic flights.
You land in Japan at 2 p.m. your time, but it's more like 7 a.m. their time, and you take an Uber or you ride a taxi to the factory. You're able to have a meeting with whoever you're meeting with for like 3 hours. You can then board a flight and get back home in time for dinner.
And in a world of super fast internet and remote calls, do we really need to be flying these CEOs across the planet at hypersonic speeds? And finally, for the nearly 10% of CEOs who are super commuters, traveling 100 miles or more to work, one study found that they consistently underperform their localized counterparts, causing their firms to lose value and their tenure to be shorter. It's even worse if they own a boat or live near a golf course. It turns out the only person who would actually fly supersonic and be home in time for dinner was the pilot of the Concorde.
I would drive my wife early in the morning to the station, our local station. She'd get on the train, commute into the city, and I would go to Kennedy, get in my Concorde, fly to London, go swiftly through customs and immigration and come out the other side and get on as a passenger on the evening Concorde out of Heathrow. And I'd get back into Kennedy, get in my car, drive up to Katona and pick my wife up at the station. She having been to work all day, and me too, I suppose.
But even for the ultra wealthy, are they going to pick speed over comfort? When you can already fly in luxury on a private jet, is the few hours saved going to be enough to entice people back to supersonic? Could there be a faster supersonic future? Maybe, but it's not happening anytime soon. And there's a lot of reasons that people should think about and be concerned about what the implications of that future might be.
This is my first time inside of a Waymo, and we're going down the windiest street in San Francisco. Even though it looks like no one's driving this car, not this Waymo, not Tesla in full self-driving, none of these cars are fully autonomous, no matter how good they seem to be at navigating the roads. Waymos only operate in specific geofenced locations. And Tesla's full self-driving mode requires eyes on the road and hands by the wheel. Whoa, don't do that. And when any of these things get stuck, they require the intervention of a human to tell it what to do.
Hello, this is Casey with Waymo Fleet Response.
So I should just close the door?
Yeah.
Okay, cool, I'm gonna do that.
Self-driving cars are coming soon to a city near you. But we still don't know how many humans it takes to drive them. So why is it so hard to get robotaxis right? And which company could be the first to unlock this trillion-dollar market? There are two main players already vying to bring robotaxis to American roads.
Waymo and Tesla have two very different approaches to autonomy, and when you see them side by side, that's extremely clear. The Waymo has LiDAR, radar, 29 cameras all around the vehicle. The LiDAR spins out laser pulses to build a high-resolution map of nearby cars, cyclists, and pedestrians. Radar uses radio waves to track how fast objects are moving and how far away they are, even through rain, fog, and dust. Cameras read colors, signs, and signals. In case you're wondering what happens if you touch one of these things, literally nothing. It's spinning at a speed that's not unsafe, and it doesn't break it to do that, but don't do that at home. Tesla has just 8 cameras, barely visible and all. Elon Musk has called LiDAR a fool's errand and something that is expensive and unnecessary.
Tesla's camera-only approach has an advantage: cost. It's way cheaper to have a self-driving car navigate with cameras and AI than to have all the additional sensors that a Waymo does. But there's a downside. Some of the experts I spoke to said the camera-only approach will never truly be safe.
If you're serious about self-driving, you don't have just a single sensor.
Using camera only is like tying one hand behind your back when you could also use a LiDAR. It's certainly taken the hard path.
And why that matters is because this car right here, if Tesla can prove that this car is safe enough and can self-drive everywhere in the country, every Tesla on the road today could become a cyber taxi overnight. Fundamentally, two different approaches to how self-driving cars navigate.
Please close the right side rear door. Thanks.
Now let's talk about what makes them different from human drivers. There's a very long list of fairly normal driving scenarios that robotaxis struggle with that aren't an issue for any normally skilled human driver. Here's one.
Teslas don't always stop for school buses.
It just carries on.
It was 100%. When we first started testing, it was 100% of the time.
That's Dan O'Dowd. He's a critical systems engineer who designed the software that runs in F-35 fighter jets and nuclear bombers.
The kids would line up and watch us run over the mannequins, the kids in the school. Their parents would come out or the teachers would come out and say, "Oh my God, it ran over that little kid who's just walking across the road."
Over the years, Dan has probably spent millions of his own dollars trying to show how Tesla's full self-driving software has major design flaws. Like Tesla's driving on the wrong side of the road.
There can be a do not enter sign on both sides of a street saying do not enter, and it'll go right down that street because it doesn't see those signs.
And even failing a driving test.
Get me out of here.
Would have failed the test.
Even after paying for 2 Super Bowl ads, Dan said he was shocked at the response.
90% agree that this should be banned immediately. Why does NHTSA allow Tesla full self-driving?
And it did make a nice splash, but Tesla didn't do a thing.
Well, that's not entirely true. The company did send the Dawn Project a cease and desist letter. Dan thinks that people should boycott Tesla until the company proves that their full self-driving software is safe.
Pull the product off the market, FSD. That doesn't mean pull the Teslas off the market. You can still drive your car. You assign 10 engineers or 100 engineers or whatever it takes to do it, and you fix that problem, And now you can go back on the road.
Before the Tesla stands jump into the comments and say, oh, version 14 of FSD is so much better, well, the Dawn project tested the latest version too. And guess what? The Teslas are still passing school buses and ignoring the school speed limit zones.
Just to be clear, they have made improvements. 1 out of every 5 times it will not stop.
But it's not just Tesla. Waymo is under investigation in Austin, Texas for passing school buses. And in Santa Monica, a Waymo hit a 9-year-old outside of a school during dismissal. Thankfully, the child wasn't seriously injured. I was holding off on explaining this until now, but for the rest of the video, there's a concept you need to understand.
The SAE 6 levels of automation. Let's start with level 0. Level 0 is a car that has no automation. That's most of the cars on the road today. Level 1 automation is when the car can steer or brake on its own, but not both at the same time. So that's kind of like the lane assist in my mom's Honda CR-V.
Wow, I really do think it is.
It's the first time you used it?
I didn't even know I had it.
Level 2 sounds simple, but it actually is more complicated. And it's where most of today's self-driving hype lives. Level 2 is when the car can steer and brake on its own, but it requires the human to still be paying attention to the road. And even though it seems way more capable, Tesla FSD is still only a level 2 driver assist program.
Oh, it gave me a warning that I took my eyes off the road for too long.
And that allows them to evade all the robotaxi regulations, because the robotaxi regulations only apply when you say that you're level 3 or above.
But here's the thing about level 3, it comes with what engineers call the handoff problem. It means that it's automated until suddenly it calls for human assistance and you need to step in right away. Level 4 is where things start to look autonomous. There's nobody in the driver's seat. And yes, Waymo is level 4 most of the time.
But sometimes they get stuck. And when they get stuck, Waymo says, well, there's just sort of phone a friend. And that friend helps the robotaxi complete the driving task, which makes them partially a driver.
Level 5 means that the car can drive itself anywhere, at any time, and under any circumstances. It's the holy grail of autonomy, but it doesn't exist yet.
And there's another thing that's keeping robotaxis from being fully autonomous: Mother Nature.
Not a lot of people on the roads today. It's one of the worst snowstorms we've had in New York in a couple of years now. But gotta go clean off my car. Comes with the territory, you know. Storm like this, when you get like a foot of snow, you gotta clean off your car a couple times.
It's so cold. It's 19 degrees.
For cameras and sensors, snow is especially problematic. It can erase lines on the road and make everything look like a blank white sheet. Plus, those snowflakes can create noise inside the LiDAR and radar sensors, and even block the cameras. Waymo says their cars are already driving year-round in snowy conditions in 10 states, including New York, Michigan, Colorado, and Minnesota, in addition to earlier testing in California. The Jaguar I-Pace Waymos already have sensor cleaning technology, and the upcoming Ojai model will build on that with improved cleaning technology for heavier weather conditions.
Are you engineering for snow now? Tell me more. Talk more about that.
So that's happening in the next release, right? The newer version of the car, right? The Ojai, is going to have cleaning technology that's better than our current version. Right. And so all of that gets us ready for driving in heavy snow.
Right. On the other hand, you can see a lot of videos online of people using full self-driving in their Tesla in snowy conditions like this one. And they say it handles pretty well.
And I am just so happy right now that FSD is driving this way in this snow.
Waymo admits that winter weather scenarios are underrepresented in their training models. Now, in order to make up for that training, when they don't have cars in scenarios like this, they've added to their simulated models to help train the cars to get better at dealing with winter weather.
Those simulations can also be used to deal with what engineers call the long tail problem.
Things like encountering wet cement, or a car hauling a tree that's swaying in the back, or a man in a wheelchair chasing a duck across the road. Those are all real-life things that actually happened. When I met with Chris from Waymo, he told me that the company's recently unveiled World model can help tackle these rare safety cases.
transform scenarios from a dry condition to a snowy condition, as an example. And this allows you to multiply the data. And what we find is that while there are many long tail scenarios, we have a corpus of data that actually has allowed us to reach levels of performance that are showing up in the result.
That was a Jaguar followed by the new Ojai model. Now that Waymo World model can help the cars learn from situations that the cars may never actually encounter in real life. And some of the demonstrations they have on their website include driving into a tornado and dealing with a charging elephant in the middle of the road.
The catch with the simulation is, if the simulation doesn't have something in it, then you'll never train against it. As a really simple example, if your simulation doesn't have any moose in it, the first time you see a moose, you're going to have an edge case you're not trained for. So simulations can help, but ultimately, if the edge case is not in the simulation, you have not really solved the problem.
So by some estimates, before they can truly say that these cars are safer than human drivers, robotaxis should expect to clock billions or maybe trillions of miles so they can see as many of these edge cases as possible.
Humans are not nearly as dangerous as the self-driving car industry wants us to believe. That's actually pretty good. We have a lot of fatalities because there are trillions of miles driven. It's just a numbers game.
But there's no amount of computing power that can predict how the public will react when something goes wrong. And that's why we're headed to the Mission District. I'm on 16th Street in the Mission District outside Randa's Market. I wanted to take you here because this is the location of one of the saddest stories in the rolling out of Waymo so far. So Randa's Market, there was a cat here named Kit Kat who was adopted by the owner and lived here and was known as the mayor of 16th Street. Everybody loved this bodega cat. We talked to some of the guys who hang out on this block and they told me some nice stories about the cat.
We would roll around over here, get on his back and
yeah,
on the stomach and everything. And
yeah,
all the homies, man. All the homies.
Yeah. So what was your reaction when you heard the news?
I didn't even cry. I was just really mad.
The story goes, at 11:30 at night after the shop was closed up, the cat was here on the curb. A Waymo pulled up to drop someone off. And right as the Waymo was pulling away, the cat darted under the car. A female bystander saw this and tried to coax the cat out, but the Waymo started to drive off, killing Kit Kat. In this case, a human driver might have seen the woman searching under the car and investigated before pulling away.
It led to a big public outcry. There were protesters. There was a media conference here with some elected officials. They now sell memorabilia, merchandise. I paid $25 for this hat. Remember Kit Kat? There's a shrine here. And why is this important? Obviously, Kit Kat wasn't the first animal killed by a self-driving car and won't be the last, but you can see how when you have something as beloved as this bodega cat, it really sets people off and it brings negative attention onto this kind of robotaxi coming through their neighborhood.
Every time I see a Waymo, I spit on it.
For real?
I'm not gonna lie.
We are gonna be meeting with Waymo this week. We're going to one of their lots. We're interviewing some of their executives. If you could say a message to them, what would you say to those people?
Do they think they took responsibility for what happened?
Right. Did they feel like they took responsibility?
They went about it right, correctly.
Yeah. In other words, they have a long way to go before they earn the trust of the people.
Oh, yeah, definitely.
Kit Kat remains a cautionary tale, but a single accident can bring down a multi-billion-dollar fleet. And in San Francisco, that already happened. Cruise, which was operated by GM, suspended operations in 2023 after one of its cars dragged a woman underneath it. She was seriously injured, and that pretty much was the death knell for that service in the city.
So I have the incident report here from the San Francisco Fire Department. They utilized the spreaders and cribbing to remove the individual, and she was later transported code 3 to San Francisco General Hospital with significant trauma. Right now I'm under an underpass, and I'm next to a parking lot, but why am I here? Look through here. You see that? This is what a robotaxi graveyard looks like. The cars in there are literally sitting around just gathering dust and grime. You would have thought that maybe they would have moved them somewhere else.
Between Kit Kat and Cruise, it's clear that self-driving cabs pose a risk to both pedestrians and pets. And even if that safety record improves, none of these companies can yet answer the trillion-dollar question. How many people does it take to drive a robotaxi? Congress pressed Waymo on where its remote assistance workers are located. Waymo says they had already disclosed this to regulators and the press, but the hearing was the first time many in the public had heard it.
In what countries are these employees located?
The Philippines.
Excuse me?
The Philippines.
So they are in the Philippines.
Yeah.
Mr. Pena, that is completely unacceptable. And here's why.
Waymo revealed they have around 70 remote assistance agents on duty. Around half of them are overseas.
So if that remote person is in the Philippines, you have some issues of jurisdiction and accountability.
But whether it's 70 workers or 700, I had a personal experience that tested the limits of what Waymo's remote assistants are able to do. I was supposed to go pick up my colleague Lloyd and then head to Mountain View to interview executives at Waymo HQ. He lives in an area with terrible cell phone service, so when the Waymo passed his house, I had no way to tell it to turn back around.
I still don't have service. And the app is not working.
Okay.
Now the app looks like this.
This turned into a 30-minute ordeal with a remote assistance team.
Even if you tried turning off and opening your data as well, it's not really working?
I'll try that.
Okay. Just let me know if there's still an issue, okay?
They were unable to get the trip started again, and I had to wait for my coworker Lloyd to show up and save the day.
Lloyd, dude, I told it to put, okay. First of all, cell phone reception in your neighborhood is not great. Lloyd, help me. Lloyd, help me, man.
Finally, Lloyd, who had cell reception, was able to order a new robotaxi, and we continued on our way to Waymo HQ in Mountain View.
Nice cardigan. Bye-bye, Waymo. All right, let's see.
Lloyd Lee writes for Business Insider about self-driving vehicles.
Really, the Smiths?
In terms of like how many humans are operating each robotaxi, it's kind of hazy because you have the people in the call centers, the remote support agents, but you also have people at the depots who have to charge and maintain these robotaxis. And then of course there's the engineers who are sort of supporting the whole robotaxi push.
In simple terms, why does it matter how often a human has to intervene in these rides?
I feel like it shows the maturity of the technology, or another way to put it, how autonomous are your autonomous cars if you constantly need a human holding its hand?
That was made brutally clear in December 2025 when a major blackout in San Francisco showed how fragile current AV systems are. More than 800 Waymo vehicles were in the outage area and experienced over 1,500 stoppages. Waymo says 96% of those stoppages resolved autonomously, but the remaining vehicles blocked intersections and created problems for first responders and other drivers. Something as common as a blackout should have been part of the simulation, and even if it was, Waymo looked like they weren't prepared. So today I'm at Waymo's San Fran depot to see how the humans behind these robotaxis are keeping them on the road. There has to be at least 60, 70, maybe 100 people working here right now. There's a big crew of people. It looks like there's a bunch of different job functions. Everyone's wearing yellow work vests, and they're servicing these Waymos as they come in. You can see the charging stations here. We've got our gloves, our spray bottles, vacuum cleaners. It would seem that they go through a ton of towels based on the fact that they have one for Wednesday, one for Tuesday, one for Monday. That's Monday's towels. 1 day of towels. And that's all the dirty towels. There's different lights, colored lights on each of the vehicles, and there's a chart that I guess is to let the workers know what kind of service each one of those vehicles requires at the time. You've got things like a biological / lost item, which I'm guessing is like, food, or maybe someone threw up in the back, or maybe there's, something that what I did, like an idiot, is leave their wallet in the back, which, by the way, I was able to retrieve. Thank you, Waymo.
Yes, thank you, Waymo. Thank you, Waymo. Thank you, Waymo.
The robotaxis do not have to be fully autonomous for this to make sense as a solution. The number is never going to be zero. If you have the same number of people involved in the robotaxi, but they're outside of the car instead of inside of the car, I don't see how you make this economically viable.
I didn't get this conversation on record, but I did meet someone while I was here who's a Waymo driver. And that means that basically he gets paid to sit in the driver's seat of the Waymo and either drive manually, and his moves, everything he does is recorded and sent back to train the data, or he's driving in autonomous mode and he does what he calls triage. So he uses these buttons on the steering wheel to send data back to the developers. One thing that stuck to me is that he told me that there are stretches, especially when you're driving around in autonomous mode, that he starts to drift off. And the front seat actually notices and buzzes or shakes him awake, which I thought was pretty funny. So while the future of self-driving cars might look sleek from the outside, there's humans at every step of the way driving these things to train them, tagging data on the back end, cleaning them, servicing them, handling remote operator calls, and getting shaken awake when they fall asleep at the wheel.
How would you characterize the moment we're in right now in terms of the deployment of robotaxis, at least in America?
People like to think that we're 99% there because there are hundreds, and in one case, a couple thousand robotaxis out there on public roads driving around, and it feels like we're almost there, that it's almost solved. It feels like it's 99% done. But I think of it a different way. The difference between having a couple hundred robotaxis and a couple million robotaxis is dramatic. There's still many, many issues with safety and deployment and scalability. And so I think of it as, well, we're done with the first 99%, but we still have another 99% to go.
Now we're up to full speed on the freeway. It's going 65. And not bad, not terrible. If it's not clear from the depot, owning and operating a fleet of vehicles is an astronomical cost. So that's why anybody who's trying to make a robotaxi business work is trying to reduce those costs as fast as possible. And their newest generation of cars are actually going to be not the Jaguar I-Pace, which costs an estimated $150K, but they're going to be based on the Hyundai Ioniq, and that is estimated to be about half the cost.
What remains unclear is how much that cost reduction will help Waymo close the gap in pricing with other rideshare services like Uber and Lyft.
So I downloaded this app, it's called Hackney, and it basically compares the prices between Uber, Lyft, and Waymo. The price that came up on the Waymo is $13.05. Just regular UberX is $23, so it's even twice because of the surge pricing, and it's got $11.91. So in this case, Lyft would have been the winner.
According to analysis by journalist Om Malik, Waymo needs to be targeting more expensive rides, like $30 a pop, just to make the numbers work on their current $126 billion valuation. But right now, it seems like Waymo is more in a spaghetti phase. They're throwing everything at the wall and seeing what sticks. In Nashville, Lyft manages the fleet for Waymo. And in Dallas, Avis takes that job. In Austin and Atlanta, Waymo rides are booked through the Uber app, but Uber is responsible for managing the fleet.
We've tried to keep all of our options open, keep all the doors open. And so we're learning a lot right now from the different types of models that exist in each of these markets, and are going to continue to explore as we expand to more cities. We recently shared that we've been doing deliveries with DoorDash.
Waymo may be taking that partnership literally. They've been paying DoorDashers to show up at stranded Waymos just to close the door.
I don't think we're at a point in time where we want to say this is the one way to do it and this other way is not the way to do it. It's so early in the widespread deployment of these things that I think it's premature to kind of declare one way or the other.
Now, Tesla's model is radically different. They're selling cars to consumers today with the promise that in the future, they'll become self-driving cabs that can earn money for the owners when they're not using them.
It will be like an Airbnb thing. You can add or subtract your car to the fleet whenever you want. Your car gets added to the fleet and it just makes money for you while you're gone. Yeah.
Markets seem to be bullish on Tesla getting their cybercab business off the ground. Morgan Stanley analysts expect 1 million cybercabs on the road by 2035. And this chart shows how they're projecting that robotaxis will take over a third of all rideshare miles in the years to come. But overall, self-driving car use will remain pretty flat. But if robotaxis remain a novelty, how will these companies deliver on their biggest promise? That their cars are safer than human drivers. Every year, there are over 40,000 deaths on American roads. That makes this country the most dangerous developed nation to drive in. That's a death rate of about 12 people per 100,000 population. There are several explanations for this, including the fact that drivers are more aggressive and distracted than ever before. The argument goes that robotaxis never drive tired or get drunk, and that they're already safer than human drivers. And as we see more of them on the road, they could reduce traffic fatalities to near zero. Waymo does have a pretty good record so far.
At least right now, on par with Uber and Lyft drivers, which is to say that they have accidents about 4 to 6 times more often than your average driver, which is an amazing achievement. I want people to understand, I think Waymo has done a very good job of getting at least on par with a more high accident population, but still they've done a pretty good job.
But what if I told you that some people have already seen enough to say that robotaxis will actually make streets more dangerous, and that they're willing to go to extreme lengths to prove it?
In 2023, as robotaxis started to take over the streets of San Francisco, a group of activists calling themselves Safe Street Rebels started staging protests. Basically, they figured out that if you take an orange traffic cone and put it on the hood of a Waymo, it can stop it dead in its tracks.
It was us showing through a very passive and peaceful object of just a cone that this technology is not as good as it seems. We never ever once destroyed a car. We were never vandals. We were also showing that the technology just in its inherent form didn't work very well.
For example, I don't think it happened here, but in LA, when you had some of these anti-ICE protests, people really took their rage out on Waymos. I don't know if that was just convenience or if that was like a targeted thing, but there's some pretty gnarly videos of people just taking rage out on Waymos.
Yeah, that wasn't Safe Street Rebel. But I do think it speaks to something that's, people are really fed up broadly with big tech right now. They're really fed up with the ways that corporations have gotten away with so much. To see how many times Waymo has injured someone's pet, injured someone's loved one, caused havocs, blocked an emergency vehicle, to see all of these times that Waymo has messed up, we have to ask who's being prioritized. Is it the driverless car companies or is it the people? And it really feels like the driverless car companies, and I think people are really fed up with that.
Adding cars to the equation never makes the situation safer. My biggest frustration that I have heard a lot is they're the future. And it's just like, we thought Laserdisc was the future.
Ren and Austin took us on a tour of their hometown to give us a look at the car-free future they're hoping to build.
Oh, there it goes. Yep, right past me.
This is a slow street right here. The intention of the design is that cars only drive to destinations on the block they enter. They don't drive multiple blocks up and down the street. You can see behind us right here a set of barriers in the street that block the incoming lane.
Yeah, I mean, you can just see with the sheer number of people riding past us, these are some of the most alive streets in San Francisco. Yeah, slow streets work. They're a very, very effective design of traffic calming, but Waymos don't act like humans, and traffic calming is designed for humans. They are not really understanding the barriers, so there can be a lot of issues.
There's one right
now. It
now.
actually looks like there's one. So this is a Waymo waiting in the middle of the intersection so that it can get into a slow street, and it's giving up.
They also showed us Sunset Dunes, which was a strip of oceanside highway that was recently converted to a car-free park.
It's just a wonderful place where everyone can come together and enjoy the beach.
There's something that a Waymo will never be able to do that public transit and biking and slow streets do, which is bring community and get people outside talking to their neighbors. Our slow streets are some of the liveliest streets in our city where neighbors know each other. They host really wonderful block parties.
If the real goal is fewer people dying on the road, autonomy isn't the only answer. It might not even be the best or fastest one. Last year, Helsinki, Finland announced something remarkable: 0 traffic deaths. Not 0 pedestrian deaths, 0 traffic deaths, period. They didn't get there with self-driving cars. They didn't wait for AI to solve human behavior. They did it by slowing cars down. City officials lowered speed limits across residential areas and the city center, enforced them with speed cameras, and redesigned streets to make driving feel less comfortable. Roads were narrowed, trees were planted closer to traffic. The city invested heavily in public transit, cycling infrastructure, and walkable streets. The logic was simple. Slower cars means fewer deaths, and data backs that up. Drop a car's impact speed from 40 kilometers per hour to 30, and the risk of killing a pedestrian is cut in half. And here's a shocker: half of traffic fatalities are the 9% of people who still don't buckle up. What if we just make seatbelts great again? As we pour billions into teaching cars how to drive like humans, places like Helsinki are quietly asking a different question. What if we just stop designing cities that let cars kill people in the first place? And that may end up being the hardest problem autonomy can't solve. So, what happens next? Waymo keeps expanding, Tesla keeps shipping new versions of full self-driving, and to be fair, there is real progress. In early 2025, Waymo reported 0 at-fault injury crashes across more than 7 million fully driverless miles. There are asterisks to that safety record.
And the reason that you're seeing very, very low highway miles out of Waymo is because this is where it's really dangerous. When you're going 65 miles an hour, this is when you can kill someone. So I do think that highway driving is going to continue to be an albatross around their neck, as is scaling. I think Waymo is, the more that they try to increase the fleet size, the holes in the dikes are really starting to show.
Right now, what we see is Tesla is not yet even into scale-up mode. They're still trying to get their technology reliable enough that they can start to scale without human drivers involved. This is not an overnight success story. This has always been a multi-decade slog. And now we're a decade or two in, and there's another decade or two to go.
So if Waymos remain a city-by-city grind and Teslas remain a driver assist system, where will we see full Level 5 drive anywhere, anytime autonomy first? Probably somewhere like the port you hear behind me. Oakland has one of the largest ports in the country, and we're standing here. You can see a constant stream of large trucks and shipping containers getting unloaded from cargo ships, coming and going all day, every day. This is one of the busiest ports in America.
I expect it's much easier to succeed, and we've already seen successes in things like transportation enclosed environments like ports or logistics hubs, things like this. Those are the easy pickings, and that's where it's much easier to have success.
You could just see these epic lines of trucks, and every single one of these guys is in their truck because they're moving up probably 50, 100 feet every few minutes. And just imagine a world where they could leave their trucks and maybe go take a break or whatever, and it would still move itself into line into the loading zone. That's kind of the dream of what autonomy would look like in a place like this.
I just felt like the robo-taxi application at the time didn't tick all the boxes. It wasn't as compelling of an opportunity.
Kodiak CEO Don Burnett worked on Google's self-driving cars. He didn't leave because the tech stopped improving. He left because trucking offered a more realistic path to real-world autonomy. Kodiak's approach reflects where most experts think autonomy will arrive first. Industrial sites like the Permian Basin, where Kodiak already runs highly autonomous operations.
We work with a company called Atlas Energy, They're a sand mining company that provides fracking sand for the oil and gas wells. The misconception about the Permian is that it's actually remote and therefore there's no traffic. These roads are heavily trafficked. There's a tremendous amount of trucks going in and out, delivering supplies, delivering sand, delivering fuel, delivering water, delivering electricity. And by the way, when I say these trucks are driverless, they truly have nobody in the cab. There's no observer, and we don't require remote monitoring. So they are truly on their own out there. We fully trust them to do all the tasks that a human would normally do in the truck, delivering across that entire, multi-hour load delivery back and forth.
In mining, in the closed industrial environments, level 5 is a thing, and it's been a thing for a long time. Look, it's the perfect setting. Dull, dirty, dangerous. You can control the environment. You can control the people working in that environment. Rio Tinto is the company I've worked with directly, but many others have followed suit since then.
Automation, at least in terms of self-driving trucks and things like that, is kind of old hat in your industry already.
Yeah, we've been on an autonomous journey for over 15 years at Rio Tinto, where we started off with building the operations center, which is right behind me here, where there's 600 people controlling the vast array of activity that occurs 1,500 kilometers away in the Pilbara. The first technology that we implemented was autonomous trucks. The way we control activity here in the control room does vary from activity to activity. For example, our autonomous drills can be operated of one person up to 8 drills. For autonomous trucks, one person can operate up to 20 trucks.
Despite the concerns and criticisms, the expansion of robotaxis seems inevitable. I even saw Waymo in Lower Manhattan. The company confirmed this car was driving autonomously with a trained specialist behind the wheel.
This is the first time I'm seeing a Waymo in New York City. This is crazy. Look at this. It's here, but it's got a guy behind it. It's coming. It's coming to New York City. This is crazy. There it goes, right outside our office.
After spending about 6 or 7 hours total in Waymos, my experience is that the Waymo driver feels like someone who's just learning how to drive. A little too hesitant, a little too heavy on the brake, and definitely making some decisions that I found to be questionable.
Oh my gosh. It's like driving with somebody who learned how to drive a month ago. People cut these cars off a lot because they know it's not a person, so they don't give a shit. And then it jerk, you know?
I'm definitely gonna get motion sickness before the end of this video. I'm gonna barf.
And every single time it does something like that, if I had an Uber or Lyft driver who did that, I would be giving them a 1 or 2 star rating. I'm sorry.
When I took a test drive of Tesla full self-driving, it just felt way less hesitant and more like a human driver.
You know, there's a couple moments in everyone's life when they interact with a piece of technology that just absolutely blows their mind. I can't believe what we experienced just now, and gonna need to take a minute to process this.
So are AVs actually safer than human drivers? That may be the wrong question.
When we say someone is safer than human, right? It's a very weak argument for the general public.
High-level statistics about safety are just not how people judge these vehicles. They judge them incident by incident, and every weird maneuver, every viral video, and every news story about a robotaxi doing something it's not supposed to do costs the industry more than any high-level safety statistic can buy back.
If you're selling on perfection, every picture makes you look bad.
So here's a different pitch for robotaxis that Phil thinks might actually work.
We try and make the fewest mistakes possible. We're transparent that we fixed it, and when we fixed it, it really stays fixed. And by the way, we're not going to hide anything. You can trust us to be transparent, to be good road users. Nobody's perfect.
Not perfect, but always improving. Then you can market robotaxis to users who have already expressed high interest in them. Parents who are too busy to schlep their kids to all the different places they need to go. And people who just never want to deal with another person in the car. And here is where I'll leave you. It's important to keep in mind that many companies have already tried and failed in the robotaxi endeavor. Argo AI, the startup from Ford and VW, shut down. Apple quietly scrapped their self-driving car program after spending billions of dollars on it. And Lyft and Uber sold off their autonomous vehicle units. But those rideshare players are reinvesting in the technology, and more companies are entering the space. Zoox, owned by Amazon, is already operating in Las Vegas and San Francisco. Tesla already has cybercabs rolling off the factory floor. Lucid unveiled their robotaxi concept, and NVIDIA wants to build the technology stack behind all of it.
It's more peaceful than humans driving.
These robotaxis will continue to be a mix of impressive, frustrating, and potentially dangerous. But whatever happens next, whenever you see a self-driving car on the road, know that right now, someone, somewhere, is behind the wheel. Since the beginning of time, men have tested their strength by lifting the heaviest rocks they could find. And there are few lifting stones as famous as this one.
The Husafel stone weighs 410 pounds. That's about the size of a small car engine. Not only might we see a new world record, we could be in the presence of a new legend. He's done it.
The thing that I noticed is that thing is heavy on the chest. It's hard to breathe. That was the hardest thing about that.
The Husafel stone from Iceland is so iconic that replicas of it are used in strongman competitions around the world. The legend goes that the triangular mass was the gate to a pastor's sheep pen. But the first person to lift it and carry it around the rock wall wasn't a man at all. It was actually the pastor's daughter. If the story's true, that makes Leafa Ingalls and Sandra Bradley some of the only women to pick up the stone in over 250 years.
It's like a puzzle you have to solve because everybody has different levers and advantages and strengths.
Come on, yes!
What's been the reaction since you've done this lift?
I can't count how many times I've read that my spine is going to pop out my back or my uterus is going to fall out.
Extend!
Elite athletes today are bigger, stronger, and can lift heavier weights than ever before. Even in the lowest weight classes, they lift twice, 3 times, or even 5 times their own body weight.
Wow. That's a wild amount of weight.
The heaviest conventional lifts of all time are somewhere between 1,100 and 1,500 pounds. And only a handful of athletes are capable of inching those numbers higher. In this video, we're doing a deep dive into all the factors making this new era of human strength possible.
How big can human muscles be? We don't really know.
And by the end, we'll answer the question: what's the maximum weight a human being can lift?
On the way we go! Ladies and gentlemen, Eddie Hall lifts the half-ton 500 kilograms!
Until strongman Eddie Hall did it in 2016, people weren't convinced a 500 kilogram or about 1,100 pound deadlift was even possible. But records don't seem to be slowing down. In 2020, Eddie's was broken by Hafthor Bjornsson, the strongman and actor from Game of Thrones.
I doubt that you're human sometimes. Yeah, people have doubted it for a long time. Yeah, but I'm true that I'm human. I tore back, remember? Oh, that's true.
In strongman competitions, the lifter is allowed to wear a suit and straps to help with their grip. This differs from raw powerlifting, in which the suit is not allowed. It could be argued that raw powerlifting is a more pure test of strength. But as you could see from this chart, all of the heaviest lifts of all time used some kind of equipment. And that allows the athletes to add several more plates to their heaviest lifts. And if we're purely talking about the heaviest weights a human can lift, an elevated bar is an easy adjustment that allows strongmen to lift way more. Thor's 501 kilogram lift was with a standard barbell that sits 9 inches off the ground. But elevate the weight to 18 inches and the world record climbs to 580 kilograms. And at 27 inches off the ground, it stands at a massive 670 kilograms. But for the strongmen looking to prove themselves, the standard bar deadlift has become one of the key benchmarks of human strength.
It's like good musicians, artists, anything, they do masterpieces and it looks like zero effort. So I think my friend Avi is a true artist in the ways and the manners of the deadlift. Yeah, just wanted to say that. Thank you. What is that in here?
Other people have argued that the ultimate test of strength is how much weight you can hoist over your head. In that case, we'll have to look at Olympic weightlifting. But compared to the recent string of record-breaking and strongman competitions, Olympic weightlifting records are a different story.
Well, it certainly felt as though all of the biggest lifts were hit in the 80s. It actually dropped off for 30 plus years.
In the 1970s, the Soviet lifter Vasily Alexeyev set 80 world records. He was famous for increasing his lifts as gradually as possible, sometimes by as little as 500 grams. Because each time he broke a record, he received a payout from the Soviet state. And almost 50 years later, the clean and jerk world record now stands at only 11 kilograms more than his 256 kilogram best. Compare this to deadlifting, where in the last 50 years, the world records have risen by over 120 kilograms.
And it's really only since 2016, there's this one guy who's turned up from Georgia, Lasha Talakadze, and he has started to break all-time world records again. And because he's a super heavyweight, these are sort of the absolute most weights that any human has ever put overhead.
He secured his third Olympic gold medal in the Paris Games.
What do you think it is that is getting him to be able to move that needle again in terms of inching up these weights?
He's like a larger scale human. He's extremely tall. So he's in proportion to the most athletic, smaller weightlifters, just scaled up. And so that allows him, because he's taller, he has a greater distance to pull the bar, to accelerate the bar. The bar can reach greater speeds.
These lifts are incredibly impressive, especially considering that Olympians are always subject to drug testing before they compete.
You think that everybody's clean, and then you learn a little bit, and you think that nobody's clean, and then you learn and you stay in the sport for much longer, and suddenly you feel like you actually have no idea what's going on.
We'll get into steroids more later. They're an open secret in strength sports, but steroid use can only enhance what's already there. With giants like Eddie Hall, Hafthor, and Lasha roaming the earth, we know that size matters. Over the past 150 years of industrial civilization, people have just grown bigger, with easy access to lots of calories, and eliminating a lot of the things that used to kill us before we could grow up. But here's the thing, science hasn't really cracked the code on what it takes to become super strong. That's partly because elite athletes rarely take the time out of their busy training schedules to sit for the kind of observation and testing that scientists like to do.
There have been case studies from very high-profile athletes in other sports, and nobody really from strength and power sports.
So that's why it was such a big deal when Eddie Hall agreed to go through a series of tests at Loughborough University in the United Kingdom.
You know, I've been treated as a guinea pig for the last 10 years of my life, really. Every day's, I'm sort of poking and prodding at myself to see what I could do with my body, so I'm just used to it by now. Here we're testing all the different variants of my muscles and my tendons and ligaments and everything.
So what did they discover?
So his overall lower body muscle mass was bigger than any individual or groups that we've measured before, more than twice that of untrained controls.
The scans of Eddie's legs are on the left, and the images on the right are of an average person.
But what was really interesting is that there was a pattern to that muscularity. Some muscles were only a little bit bigger actually, maybe only 25-30% bigger than untrained controls. Other muscles were 3 times as big, so 200% bigger.
3 specific muscles in Eddie's leg were much larger than anybody else. The sartorius, gracilis, and semitendinosus, also known as the guy rope muscles.
The 3 muscles that help provide stability to the thigh and hip.
Muscles that are really important for doing, you guessed it, really heavy deadlifts. The team also discovered that when compared to other professional athletes, Eddie is still in a class of his own.
Quite similarly, with his counter movement jump power output, his peak power output, he was about 40% more powerful than the highest values in the published research literature that come from professional basketball players.
On this chart, Eddie's the X in the top right corner. When it came time to test the strength of Eddie's deadlift, he may have accidentally given us a preview of where human strength could be headed next.
Going in. 3, 2, 1, pull! Let's go!
That's 7,483 newtons, so that's about 750 kilos.
That's equal to a force 250 kilograms more than the current world records.
I think I'll leave it to that, guys. They're pulling me now. Is that all right?
Yeah, that's fine.
So now we're getting a little bit closer to understanding the idea of theoretical maximum human strength. Take a massive human being, train them in a few specific body movements, maybe feed them a little bit of steroids, and pretty soon we'll have somebody who can deadlift 750 kilograms. Sound about right? Well, what if I told you that the Guinness Book of World Records records the heaviest lift of all time at over 3 times that amount of weight?
Who is gonna tell the child about Jesus? Who is gonna tell the child about God?
That record belongs to this guy right here.
Hello, I'm Greg Ernst, and I live in Nova Scotia. I'm a farmer and a blacksmith, and I guess I'm the guy so far that the man that's lifted the most.
He also sings gospel music with his family, in case that wasn't clear. In 1993, Greg set a world record with a type of lift that you just don't see that much anymore.
They're in the air. For the past few years, Greg seems to be lifting everything and anything and breaking records along the way. The oxen may not be impressed, but the crowds keep coming back. Just 2 weeks ago in a driving rainstorm at this country exhibition, Greg did something no man has ever done. Using a specially built platform, he lifted 2 Ford Festivas and their drivers. Total weight, 5,340 pounds.
There was press there was a lot of people gathered, and it was a real spectacle. So what did you do to prepare for that, and what do you remember about the day?
It was wet. It really rained hard. It was so hard to keep your hand, the handboard dry enough that your hands wouldn't slip off. That was the big problem.
And you got big hands. Let's see your hands. You've got gigantic hands.
Anyway.
The reason you've probably never heard of Greg's record is because a backlift is sort of an old-timey strongman thing to do. It's the kind of lift that you might see before the days of television, when strongmen would travel around, attracting crowds to watch them do their feats of strength. In 1957, legendary American strongman Paul Anderson allegedly lifted 6,270 pounds, almost 1,000 pounds more than Greg's record. But it was never verified. Unlike Greg, who had people from the Guinness Book on site when he did his lift in 1993. Why do you think that the backlift is not really part of most strongman competitions, and do you think it's something that should come back?
I think it should come back.
Greg only lifted the cars about an inch or two off the ground. In this footage, it's almost imperceptible.
I'll tell you the reason, and this is what, if there's anybody listening that wants to try this, which I recommend, but you just got to be careful. And that is, if you happen to hyperextend those knees, like you get to the top and you bend, you're a little back bend in that knee, and that weight comes down, it'll tear your knee. It'll just destroy your legs.
And in addition to that high risk for injury, it's just less impressive than some of the events you can see in strongman competitions today. None of these events approach Greg's record, but they're just really cool to watch. But the Guinness record isn't the only thing Greg is known for. Remember the Husafell stone? He set a new world record with that as well in the early days of the World's Strongest Man competition. It wasn't seriously challenged until almost 30 years later, when Hafthor came onto the scene. And there was one really important thing that Greg says set him apart from his competitors.
They always trained and competed completely drug-free. And it was a huge disadvantage when you were at World's Strongest Man, because there was virtually nobody who did it that way. Well, my strength was on the farm. So I had dairy cattle, we had some beef, so I had access to all the milk and meat that I wanted. And so, for instance, in the height of my training, I would down a 5-pound roast, a beef roast a day. I would down 2 gallons of milk a day. If somebody comes along and does it like I did it, fine. Like as far as I'm concerned, the guys with superior nutrition, if they should, to be on par equal, should be about 7,000.
Just to make that clear, Greg's saying if we could get someone with modern nutrition and training to do a back lift like he did, that lift could clock in somewhere over 7,000 pounds. That's almost 6 times the weight of the deadlift record.
And so they're just it's just something that your body is hooked up for.
And you're saying your body was hooked up for this back lift?
Yeah, my body was. There's 2 things I was pretty bloody good at, and that was rock, stone lifting, and this back lifting. And there's some guys that are hooked up for overhead pressing, for instance, or bench pressing. They can't deadlift what they can bench, but they're hooked up for bench. And then there's some guys that are great deadlifters.
What Greg is talking about is a concept known as leverage. Certain body types are just built differently, and those special proportions can give someone an advantage when it comes to lifting weights. And that's why I called this guy.
Hey, Dan.
Hey, what's going on, Mike?
Nothing. So just got back from work.
Awesome. What do you do for a job?
I work at a steel fabrication shop. I run a CNC and weld, mostly.
We're here in Allentown. We made it to Allentown, Pennsylvania, and we're going to go meet with Mike Coons, who is a power lifter, record holder, and is going to help us understand a little bit more what goes into the strength requirements to lift the biggest amount of weight possible.
If we're talking about the maximum weight you can lift compared to your body weight, Mike is the person to beat. He set a powerlifting world record for his raw squat of just over 250 kilograms. That means he lifted over 4 times his own body weight. And that's something these bigger lifters can't compete with. Compare that to Eddie Hall or Hafthor, who can only squat 2.5 times their body weight.
Okay, so let's go inside.
Mike's competed in powerlifting since he was a little kid. We spent a day with him to see how his unique proportions affect his strength.
Hey, Mike.
Oh, hey, Dan.
Good
How's
to
it
meet
going,
you, man.
man? Nice to meet you.
Yeah.
Yeah,
I mean, that's got to weigh what, like 70 pounds? No, more.
I'd have to, at least. I'd have to look at the papers and stuff to see. But yeah, this stuff's, and this is, grade A572 steel, so it's dense.
Yeah.
And stuff and everything.
So in other words, this is part of your warm-up, right?
Yeah, I think if not for powerlifting, a person of my size wouldn't fare too well in this line of work.
For sure. When you were, let's say when you were a kid, when you first started lifting, how old were you?
I started training about 10, 11 years old.
Mike's first coach was his dad, Don.
Hey, I'm Dan.
Hi, Dan. I'm Don.
Good to meet you, Don.
Glad to meet you.
Yeah. This is Mike at 9 years old before he started training.
And he came home one day from school, visibly upset, and I said, "What's the problem?" And it was his classmates were picking teams for sports, and he's always the one that gets picked last. And he said that they picked for baseball, I'm the last one. They picked for football, I'm the last one. They picked for basketball. I said, "Well, you're not built for basketball." He goes, "Well, what am I built for?" And I'm thinking, "Okay, Dad, think quick." I said, "You know what? You're built for power. And we're going down in the basement and lift weights. Let's go." And that's how it started.
All right. So this is it. This is the dungeon.
This is it. This is the pit.
So what do you have down here? That's
Well, we have a squat rack here, so we do our barbell squats in here. And the crossbars in case we miss.
Right.
All right. I have a chin-up bar here. I do chin-ups, pull-ups, and I also do inversion.
This looks about the size of like the kind of plate you'd have at like a Blink Fitness or something like that. But this is 100-pound plate.
Yeah. And these are in Yorks run heavy. You know, if you stretch this,
this
stretch
feels
that.
stretchy. This feels stretchy.
And try the squat suit.
There's absolutely no stretch in here. Take this one back. There's no stretch in this, and the idea is that it's keeping the hips tight, right?
Correct. Yep.
That's the idea of this. So, how would you describe the way that his body works in how it helps him for powerlifting?
Well, his range of motion is advantageous to the barbell squat and to the bench press, and it's very disadvantageous to the deadlift. The best deadlifters have long limbs and a short spine. Mike's just the opposite.
So to see how that works, it was time to hit the gym. We came to this gym to see how Mike's leverages give him an advantage in two exercises, the squat and the bench press.
When I was younger, I could warm up quicker, but now that I'm getting older, gotta throw a couple more sets in, get everything nice and loose.
We slowed down this footage to see how big of a difference it is between Mike's squat and mine. He just has much less distance to cover based on his proportions.
So basically the point, yeah. So you're missing it's like
degrees.
About a 12 degree missing from straightening out, full extension. Plus you're also jacked, so.
It's like when people say, other powerlifters, I wish you had your leverages. Yeah, until you have to use equipment or you want to grab something on the top shelf at the grocery store. Then you don't want my leverages. Then you see if you want them then.
And it's the same story with Mike's bench press. But here is where Mike's body starts to work against him. This motion technically should be able to move the most amount of weight because you're engaging your back, your arms, and your legs. Here, Mike has to start bent over the bar, which makes it harder to initiate the lift and requires a bigger surge of effort at the beginning. When it comes to the deadlift, a short torso can handle a much heavier load. And that's why Stuart Jameson has been called the most anatomically perfect deadlifter of all time. The Scottish athlete was born with spina bifida, a condition in which his spinal cord failed to develop properly. And he's missing half a rib cage. But the length of his limbs, in comparison with his short torso, gives him the perfect leverages for deadlifting. So now that we understand the concept of leverages, let's return to the original question. What's the maximum amount of weight that a human being can lift? Right now, the world's strongest men are competing to break Hafthor's record and trying to deadlift 505 kilograms. The good news is that athletes like Thor and Mitchell Hooper, the Arnold Strongman winner for the last 3 years in a row, share a lot about how they train. These men will soon face off in a competition to see who can lift 505 kilograms.
I will pull 505.
Now, the dates and location, that's still being finalized.
Mitchell has outlaid his plan on his YouTube channel.
It's going to be a lot of volume and bodybuilding to grow some muscle mass in two particular areas for me. One is going to be my legs, and two is going to be my spinal erectors.
And meanwhile, Hafthor is already making a 460 kilogram lift look easy. A lot of this training is not rocket science. It's using the basics of what science knows about how to build muscle, by approaching maximal effort and strategically adding weight to get closer and closer to a goal. It also requires proper nutrition and a lot of calories.
Yes, I cook all the food for Hafthor every day, 6 days a week. He has one cheat day.
Thor consumes nearly 10,000 calories daily, That's over 3 times the intake of an average American.
350 gram rice, 125 grams tenderloin, 100 grams vegetable.
His go-to beverage is a smoothie made with Greek yogurt, orange juice, and olive oil.
I drink that with the meals most of the time.
And another drink with frozen berries and almond butter.
It's really nice. You blend together, it's like a dessert in the evenings.
It also involves a lot of back and leg strengthening exercises. Then there's the idea that just having someone to compete with is what drives elite athletes to lift heavier and heavier weights. Science backs this up. A 2015 study found that when presented with a physical effort task, study subjects performed better in a competitive environment when they thought they were competing against another person. That effect was more pronounced among the male test subjects. One thing that all strength competitors have in common is that they're able to override an important part of the brain that stops them from lifting heavier weights. The neurological system controls the muscles of the body. If the brain senses a weight is too heavy, it overrides the muscles and shuts them down to avoid injury. Reducing these neurological inhibitions can lead to bigger lifts. Just ask Eddie Hall.
I had to take myself to a zone where no other man has been. I wasn't there. I wasn't in the arena pulling 500 kilo off the floor. Basically, I trained my mind to a point where I was able to picture myself on a motorway in a car accident with my kids trapped under a car, lifting a car off of my kids. And it wasn't until I locked out that deadlift, it's almost as if I just woke up.
It's not just elite athletes who can override the brain's control over the muscles. There are countless urban legends of regular people exhibiting what's known as hysterical strength, a sudden, almost superhuman burst of power triggered by adrenaline. These hormones act like rocket fuel for your body. Your heart pumps faster, your lungs gulp oxygen, and blood floods your muscles. It's fight or flight mode, and suddenly your muscles can contract harder and faster than they ever could before. By harnessing this hysterical strength and overriding the body's safety limits, athletes can push even harder, activating more motor units in their muscles and building strength that's closer to their true maximum capacity. So where do we go from here? Are we done when it comes to pushing human strength to its limits? Not quite. There's one more area we need to discuss, the elephant in the room: steroids. Performance-enhancing drugs are at the center of controversy in strength sports. Athletes from bodybuilders to strongmen commonly use these substances to boost their strength, recover faster, and build muscle more effectively. A study from 2012 showed that anabolic steroids could increase strength by about 5 to 20% in the test subject. And it's been estimated that as many as 4 million Americans regularly use anabolic steroids for athletic or cosmetic purposes.
I know for damn near a fact that essentially no one at the top of strongmen is natural. When you're asking people if they're natty or not, you're asking them to admit to the commission of crimes. And knowing the legal landscape that athletes have to traverse, I would consider highly discourteous and impolite to ask athletes on camera if they're on steroids or not. I think it's absurd.
There's no denying that PEDs are prevalent in strength sports. Many top athletes like Thor Bjornsson have admitted to using them. And while there's a stigma around their use, the question arises, what if we removed the stigma? That's where the enhanced games comes in. Dubbed the Steroid Olympics and pitched as a byproduct of Trump's America after huge investment from Donald Trump Jr.
The media has claimed the enhanced games aren't possible. But in Trump's America,
the impossible is what we do best.
The enhanced games, a new Olympics for a new golden age.
And they want to run events where doping is completely allowed.
I believe that all human beings are enhanced. We're almost cybernetic beings now. We have an almost symbiotic relationship with digital devices, particularly mobile phones. And so I think of our objectives in the enhanced movement as building superhumanity. And I define superhumanity as where we are no longer limited by our biology.
Aaron believes that performance-enhancing drugs won't just enhance strength. They'll allow athletes to reach new limits that were previously thought impossible.
I think world records are going to be demolished.
But when so many in strength sports are already taking performance-enhancing drugs, the question is, how much further can we actually go?
I would say, like, realistically, what someone could survive for 8 weeks of this kind of thing is 3 grams of testosterone. Your body weekly makes about 75 milligrams, to put that in perspective. Take, as many IUs of growth hormone as you could take until you have so much body water that you have sleep apnea and you can't sleep anymore, or your hands don't close anymore because you have so much body water on your hands that you can't actually grab a deadlift bar. I've only known a few people to do something like this, and any given day that they wake up is a blessing to them, I'll say that. No one's having any fun anymore at this point, by the way. But you will get stronger. Holy shit, you'll get stronger. Yeah.
There you go. He is tearing into this thing.
But even with this perfect balance of genetics, advanced nutrition, and performance-enhancing drugs, when we've already pushed our bodies to the absolute limit, any advancement on our current records is going to be incremental.
In the deadlift, it does depend really on how you measure the deadlift, so on and so forth. But I think something like a 1,200 pound deadlift, maybe 1,100 to 1,200 pounds without straps, I think is possible. You would say, that's not a lot, but what we see with lifting as it gets heavier and as it approaches the human body's limits is that it gets exponentially more difficult to gain strength.
Big drag. Come on. Let's go for the record. Come on.
And so really, it's easy to look at a world record in the squat of roughly 1,100 and say, yeah, someone could do 1,150, but people have been trying for a long time that it just does not work out like that. So only by injecting a ton of variation and new talent into the sport can we see, with many years, the numbers climb to such high levels with sort of unmodified humans as they typically present in the world.
Oh my God! Wow! Come on, judges. That's a good lift. Yes! Ladies and gentlemen, you just witnessed history. You just witnessed history. Look at that crowd, too. Wow. Never been done before.
Have you ever wondered how deep we could dig into the Earth?
No one's ever gone deeper than 12 kilometers, which is about 7.5 miles. That's deeper than Mount Everest is tall. And that took the Soviets 20 years. Still, it's just a scratch on the surface, a mere 0.2% of the way to the Earth's core. It turns out that the deeper you go, the more the Earth pushes back. But new technology could make it possible to dig further.
Whoa!
Isn't that insane? It just started to fly apart. Just so you could see how this rock became literally glass. And this could be the ticket to unlimited clean energy.
Just depths down to 6 kilometers, that you could produce 1,400 gigawatts of new geothermal power. That's bigger than the current US power grid.
So can these drilling techniques make a 20-kilometer hole possible? And how far down can we actually go? Remember the space race between the US and the USSR? At the very same time, another race was underway. Not toward the moon, but deep beneath our feet. And this time, the Americans didn't win. The ultimate goal was scientific. The US started with Project Mohole in the 1960s,
which hopes one day to drill a hole through the crust of the Earth and to find out what's down there.
The idea was simple: drill through the ocean floor, where the Earth's crust is thinner, and reach the mantle. In theory, it was the fastest way down. To find a suitable spot to dig, researchers actually dropped bombs into the ocean.
3, 2, 1, 0. Over the side, over the side. The charge is over the side.
It doesn't get any more American than that. Then they used sonar readouts to measure the thickness of the Earth's crust.
But after years of work and millions of dollars, it made it just 183 meters into the seabed. That's less than 2 football fields. The project was eventually cut short due to lack of funding, but the techniques they developed led to a boom in offshore oil drilling.
Meanwhile, the Soviet Union began drilling on the Kola Peninsula in the Arctic Circle. Back then, researchers expected to hit 15 kilometers, about 9.3 miles.
But after 20 years of drilling, they reached a depth of 12,262 meters. That's deeper than the deepest point of the ocean, the Mariana Trench, located in the Pacific Ocean.
Since then, there have been oil wells that dug for longer stretches, like the Al Shaheen well in Qatar and one in Russia. But this type of exploratory drilling doesn't actually go straight down. These types of wells often veer sideways for long stretches looking for those reservoirs of hydrocarbons. So to this day, the Kola borehole remains the deepest vertical hole.
Kola was sealed with a metal cap and abandoned. It looks like this. One of the reasons the drilling was forced to stop is because the team encountered higher temperatures than expected. And this is the biggest challenge when it comes to digging deep: heat. Because the deeper you go, the hotter it gets.
As we get below sort of 12, 15, 18,000 feet, we're getting into very hot formations, very high temperatures where actual drilling tools are struggling to survive.
So if we want to go deeper than Kola, we need tech that can withstand temperatures that rise about 25 degrees Celsius per kilometer. Look at the geothermal gradient and you can see the heat increase isn't linear. Things get super hot long before you reach the mantle, a layer of Earth that no one has yet hit. As you go deeper still, temperatures can climb into the thousands of degrees. In fact, 99% of Earth's mass is hotter than 1,000 degrees Celsius. But that heat is also exactly what makes geothermal energy possible. Because if we can tap into it, it becomes a near limitless source of clean power. Right now, geothermal meets less than 1% of global energy demand. But if the technology keeps getting better, geothermal could cover up to 15% of the world's new electricity demand by 2050.
So how does it work? Inject water deep underground or dig into existing reservoirs, then use heat from the earth to turn it into steam. That steam spins turbines and generates electricity.
Unlike solar and wind, geothermal could provide electricity 24 hours a day and all year round. This is exactly what happens in places like Iceland, where volcanic activity brings a lot of that underground heat closer to the surface.
In Iceland, they actually made contact with magma at only 2.5 kilometers below the surface.
Iceland's large-scale shift to geothermal energy was driven by the 1973 oil crisis, when rising prices and geopolitical instability highlighted the risks of energy dependence. At the time, half of the homes relied on imported fossil fuel for heating, which was expensive for the country.
So Iceland turned underground. Today, nearly 30% of the country's electricity comes from geothermal, and about 90% of homes there are heated this way. And Iceland is not alone. Take a look at this map. Geothermal shows up all along the Ring of Fire, where tectonic plates converge. But there's a catch. Most places where geothermal energy works only dig down about 2 to 3 kilometers because that heat is close to the surface. Now, if we wanted to make geothermal work in more places, we're going to have to go much, much deeper. That's why we're in Houston, Texas today, and we're going to a company called Quaise that's digging deeper using literal energy beams to vaporize rock.
All right, so this is where the magic happens.
This is where the magic happens. Quaise is a startup with a very ambitious goal. They want to be able to drill down to 20 kilometers underground. At that depth, the temperature can reach up to 500 degrees Celsius, which is enough to destroy any kind of conventional drilling equipment. That's why they're using something called millimeter wave. And the idea behind it is that it's using a special kind of technology that comes from fusion energy to literally shoot at the rock and vaporize it, melting it into glass. In the simplest layman's terms possible, what is millimeter wave drilling?
Millimeter wave drilling is using microwave to do dielectric heating to get to very hot rock.
Conventional drilling uses a mechanical bit to pulverize rock, but at extreme depths, It gets harder to power the system, and it breaks a lot. Quaise uses electromagnetic energy to melt rock, and in theory, the millimeter waves maintain their power even over long distances. It took MIT over a decade to develop this technique in a lab. The device that creates the energy beam hot enough to do this is called a gyrotron, and it actually originates in nuclear fusion energy.
It actually is the device that converts electrical power to microwave power. That's important for us because it's able to make upward of a megawatt of microwave power.
You can see that the magnet's on because it's using electromagnetism. So apparently, I don't know what would happen. Would it suck? It would suck our cameras right to it, or
it could disturb some of it. Yeah.
Yeah.
We don't bring our phones in there. We don't
Right.
bring any kind of tools that are magnetic in there.
Oh, okay. So it could fly.
It's like an MRI machine.
Oh, it's like an MRI. So yeah, you know what? And actually, if you hear, I'm gonna put the microphone closer to there. If you hear, it actually sounds exactly like an MRI. If you've ever gotten an MRI, so listen to this. That's actually the sound of the cooling system. The gyrotron's superconducting magnet needs to stay near negative 270 degrees Celsius to function properly. Quaise channels the beam through a hollow pipe that looks like it has screw threads inside.
So what you see here is the waveguide, and so the millimeter wave is actually going inside there, all the way to the bottom.
So basically, Henry, this kind of pipe is what's going to be going all the way down any hole you dig, right?
That's right. So we start with a conventional drill rig to drill as deep as they can, and then we come with our technology.
So the Quaise approach is less like drilling and more like burning a hole through the earth. In theory, this solves one of the biggest problems. If nothing touches the rock, nothing overheats.
The way we address it is that we're not putting equipment down hole that could be subjected to the temperature that could damage or that could fail the drilling process in that regards. And so we're not obviously eliminating the heat. Obviously we want to get to the heat, but we're able to continue drilling in spite of the heat in that regards, right?
Here's why they want rock that hot. At those temperatures and pressures, water enters a fourth state called supercritical. It's not quite gas and it's not quite liquid, and it carries far more energy than steam. Quaise says a single supercritical well could produce up to 10 times as much energy as a conventional geothermal project. And Quaise gave us a live demonstration on how they plan to reach it. We're gonna put in earplugs, not because of the millimeter wave, but because the compressed air that comes into the system is very loud. So I'm putting in earplugs right now. Whoa! Isn't that insane? The light is completely bright. I guess you can see how the air is pushing all the other stuff out of the way. Wow. Okay, 30 says 30 more seconds to go. Wow, that's pretty cool. That's it. Oh man, that's so cool. And you could see it's like lava cooling, right? I would say the heat hitting my hands right now is probably like, a campfire that has died down. Not hot, not too hot to touch. I could still hear it crackling, which is kind of gnarly, but we're gonna, just so you could see how this rock became literally glass. If the drilling thing doesn't work out, maybe you guys can use this to get into a bank vault or something. I don't know.
Well, we said that we could just make ashtrays. I know people don't smoke anymore, but that would be an awesome ashtray.
To understand what they might encounter deep underground, Quaise hauls huge chunks of rock into the lab. We're out back at the lab now. These are 10,000-pound lobes of rock, and they represent the different kinds of rock that Quaise might encounter once they start digging down. They use these for testing, and they're very heavy and very expensive to get here. How the hell do you move these things?
It is incredibly expensive. Obviously, you need a big forklift that can actually carry the weight. But it's also incredibly expensive in terms of just getting from the quarry of this size to us as well. And it's just part of the business.
But even if you solve heat, there's another problem: pressure.
There are even more challenges that you have to deal with when you're digging super deep. And in order to show you what that looks like, we came to the Weiss Energy Hall here at the Houston Museum of Natural Science. So we're gonna take you around and show you a couple of exhibits that show you in a way that you can't see anywhere else. So what you see above me is a gigantic representation of a drill bit coming down a borehole. Obviously, this is probably, I don't know, 30, 40 times the scale, but it gives you a sense of how these rotating bits create a momentum going down into the hole, removing material and pushing it out towards the sides. So once you're getting down deeper and deeper, the rock isn't just hot, it's also heavy. That's what engineers called lithostatic pressure. At 10 kilometers down, you're under 40,000 pounds of pressure per square inch. You're basically trying to hold something open that wants to close. So what engineers do is something that might seem counterintuitive. They're actually filling the holes that they dig with drilling mud. And this drilling mud does three things. First of all, it cools the bit. Second of all, it lubricates the entire system. And third of all, it counteracts the pressure that's acting on the borehole as they go deeper and deeper. What this display is showing is that this mud has a viscosity that's meant to slow down the flow of the balls going downwards. And you could see how getting that and dialing that in just right is important to keeping the borehole stable. As you go deeper, something even stranger happens. The rock stops acting like a solid block and starts acting more like plastic. That's where casing comes in, because it's holding up the sides of the borehole as you go down and allowing you to drop a narrower and narrower channel of pipe down to reach those deeper depths. So as you could see from this example, we've started out with the widest possible drilling bore, which is 16 inches, and it goes all the way down to 5.5 inches.
Quaise believes their system could also solve the casing issue. As the rock melted by the millimeter waves cools, it solidifies into a glassy lining around the borehole. That creates a hardened layer that will help keep the hole stable.
Just to feel the texture of it is that I do feel that volcanic glass feel. It reminds me of, when you had a piece of obsidian. If you ever had a rock collection at home, that's really what it feels like.
In other words, it's a sort of ready-made casing. But can this work at extreme depths? Over the years, Quaise has proven they could dig past 100 meters, and now they've set up a test site in Marble Falls, Texas, where they're aiming to reach 1 kilometer by the end of the year.
We really want to show that we're going to do 1 kilometer, and it's really to show that we're very close to our goal of 10 kilometers. It's a 10x more, but 1 kilometer really gives you that depth where it is a viable option from a field point of view.
We hit the road to find out.
This morning, we were heading from Houston, Texas, where Quaise's lab is, to their test site in Marble Falls, which is on the other side of Austin, where Quaise is actually bringing their technology to life in the real world. I'm standing at the edge of a granite quarry, and you could see why Quaise would select this site to test their technology. Behind me, you can see that there's layers of sand and clay that have accumulated. That's called overburden. But not much further down, you've got this nice pink granite everywhere. And what Quaise is able to do is, without digging too deep, they're able to get to this granite layer and start using their millimeter wave drill to really get through it. This is a perfect site for Quaise to start proving that their technology works on the hardest rock that is found in the deepest layers to get to that supercritical geothermal.
This is the first location where Quaise has taken their technology out of the lab setting and into the real world.
And obviously it's a work site, so I gotta have my hard hat and my safety glasses here. Okay, let's go.
The gyro rig here can run on diesel, but for now it's connected to the grid.
I wonder what your monthly electricity bill is.
It's not great.
So Steve, this hole is going to be the 1 kilometer hole?
That is correct, yep. So we'll be up and drilling in about 6 weeks, and then we're expecting to hit it in the summer. So we're talking maybe 2 months to get to 1 kilometer on this.
They're gonna take this wireline camera and they're gonna drop it down the hole that's existing. So we're gonna get an inside peek into the beginning of the 1 kilometer hole. What's interesting though is that the sides of this don't look like what we saw in the lab, like more vitrified. Is there a reason for that?
We are able to go that route as well.
faster without it.
So you don't need that hard shell to prove the point of what you're doing.
That's correct.
Got it. There's another problem with drilling deep into the Earth. We don't actually know what's down there. Most of what we can tell about the inside of the Earth comes from seismic waves. How they travel and bend or slow down or speed up tells us what the different materials could be under the ground. We saw how some of this seismic exploration works at the museum. So you could see on this cube, it's representing different layers that could contain hydrocarbons, which is more for the traditional, conventional fracking industry. But this is the kind of seismic survey that you might see to understand what's below as you go deeper and deeper into the ground. And this is also part of this demonstration.
Yeah, this is a real piece of, they call it scenic sandstone, and this is a real geophone. This is one of those things that they stick in the ground. They just sort of drive it in like a stake, and then it picks up sound waves. So this is a clapper here. You can see this is a sound readout, and that's picking up kind of all the way across the frequency spectrum. This is going from 200 hertz up to about 1500 hertz. And you can see if I stomp, it's making more of the lower frequencies because I'm stomping, but it's picking it up. I mean, it's pretty sensitive.
But scientists keep discovering new layers, like the potential of a core inside the core of the Earth. For example, when scientists started the Kola super deep borehole, they thought they'd know what they'd hit. Based on seismic data, they expected to find a layer of basalt. Instead, they found water and hydrogen gas. In the US, the deepest hole ever drilled, the Bertha Rogers well in Oklahoma, had to be stopped when it hit molten sulfur and broke the bit. So the deeper we go, the less certain things become, and every surprise pushes the machinery to its limits. And all this drilling can create unexpected outcomes, like earthquakes.
I would say that if you want to create an earthquake, you can create an earthquake. But there is a really widespread engagement with the fact that that is totally not an acceptable outcome.
In November 2017, a magnitude 5.5 earthquake struck near the city of Pohang in South Korea.
Later investigations concluded that it wasn't a natural event. Rather, the earthquake had been triggered by an experimental geothermal project.
The quake left 1,800 people displaced and 135 injured. It also caused at least $123 million in damage.
The nation's energy ministry expressed deep regret and said it would dismantle this project. Prior to that, the most notable earthquake induced by exploration for geothermal was in Basel, Switzerland. In December 2006, a 3.4 magnitude earthquake led to minor building damage. But the operator's insurance company paid out over $7 million in claims and eventually shut the project down. What about this idea that drilling, I mean any kind of drilling, but this idea that drilling can create seismic activity that can create earthquakes, and how do you mitigate that?
Yeah. So to be clear, the drilling aspect of it doesn't create any type of seismic. It's obviously when you try to do what we call the EGS aspect, when we're actually connecting between the two wells is where potentially you could have these type of issues. Now, the oil and gas industry has matured this significantly where now there's a regulation in place, there's sensors in place to make sure that you never go above a threshold that's unacceptable in that regards. Really, that threshold is the same threshold as what you typically see in a football game or a rock concert. That's the threshold in which basically the standard is now. We don't go above.
In terms of a vibration.
In terms of vibration, things like that. So it's very well managed in terms of the level which is acceptable in that regard. So we never cross that threshold.
Another challenge for expanding geothermal is cost. Drilling deeper is slow, risky, and more expensive with every kilometer. Because it means more rig time, more crew, more wear on equipment, and more of a risk of failure. In fact, most of the time in conventional drilling is spent pulling up the rig and replacing a damaged bit. The core problem is upfront cost and uncertainty. You have to spend tens to hundreds of millions of dollars before you will know if a well will actually produce usable energy. That makes deep geothermal difficult to finance compared to solar, wind, or even conventional oil and gas. Historically, projects like Kola cost on the order of $100 million, and that's not even adjusted for inflation.
So the economic constraint isn't just, can we drill deeper? It's, can we drill deep enough, fast enough, and cheap enough to compete with other forms of energy? That's a yes, according to the CEO of Quaise, who recently testified at a congressional hearing.
So normally when you're drilling, you are trending in the $1,000 to $2,000 per meter. That's typical in oil and gas. It's cheaper in mining because it's a different use case. So What happens though when you go deeper and hotter is that $1,000 to $2,000 per meter starts to blow up exponentially on you. To give you a sense, you can get as high as $10,000 to $20,000 to $30,000 per meter to continue to make progress once you're below 3, 4, 5 miles. So we're trying to just skip that $1,000 to $2,000 per meter regardless of the depth, because that's what makes it economically viable and accessible.
And Henry told me that once a Quaise geothermal plant is up and running, it will prove more economically viable over time. The industry term for that is levelized cost of electricity. It's basically the cost per unit of electricity that a project needs to break even over the course of its lifetime. Quaise has an LCOE calculator on their website, and what it does is it allows you to go to a map of the United States, put a pin anywhere to get a cost of what a geothermal project would have in your area. It bundles everything into one number: the upfront costs to drill and build the project, the ongoing maintenance costs, fuel costs, financing costs, and basically the overall lifetime output of that energy project.
The amount of cost to drill a hole is about 20% of the overall cost of making geothermal. So the better answer is we think that the way we're going to make electricity, we can get these levelized costs of energy down to about $50 an hour, $50 per megawatt hours.
A price point of $50 per megawatt hour would make geothermal very competitive with new wind and solar projects.
Do you think that your first commercial project would come close to that number?
We think our first project up in Oregon will be about $100. And then by the time we get to the end of a kind, we're down to 50.
So far, investors hesitate to back up such problems. And the paradox is that because the costs are high, it hasn't scaled yet. But it won't scale without investment. So how do you break that cycle? This is where oil and gas comes in, because geothermal isn't completely new. It's built on top of an industry that already exists. Up to 80% of the investment required in a geothermal project involves capacity and skills that are common in oil and gas. And today, a large share of that workforce comes directly from the oil and gas industry.
There's 2,000 rigs around the world. With all the rig hands and all the people that know how to operate it, we basically give them a new set of tools.
In fact, some of the people we met here working for Quaise come from fracking. We're in the drilling cabin, AKA the dog house, and I'm here with Mike, Ethan, and Sam, and these guys are on site. They're living nearby 15 days out of the month, 5 days off, but they're committed to this site and they're gonna be the ones that are making sure that this hole goes down to 1 km. So I just wanted to talk to you guys because you guys could be part of a new wave of energy. Do you ever think about that and like what that might mean for, you know, for the future of everybody?
Supercritical seems like the major unlock to take geothermal to the next level. And there's some companies dabbling in it, kind of researching it. Quaise attracted me personally just because they're full-on committed to making super hot, supercritical happen.
All the basic tools are the same. The expertise is similar. And even the techniques like horizontal drilling and hydraulic stimulation come from fracking, which means if geothermal scales, it'll likely use oil and gas infrastructure. And that matters because oil and gas is one of the few industries with the capital, equipment, and experience to drill at this scale. And we're already seeing interest. Chevron recently announced a joint venture with Baseload Capital. They have a fund focused on US geothermal development opportunities. Aramco announced they'll look into geothermal in the Middle East, and the current presidential administration has opened up public lands to a number of geothermal projects. But so far, investment has been limited compared to the trillions spent annually on fossil fuels. The industry is still waiting for a breakthrough, and until that changes, deep geothermal isn't just a technical challenge, it's a financial one.
So instead of going deeper, some geothermal companies are changing their strategy entirely.
I would say the main reason people haven't gone deeper is there hasn't been a reason to. You know, oil and gas is found in shallow areas, and so the only reason to really drill past 10 kilometers is, you know, do a research well, and I'm sure you found a couple examples of that.
Companies like Fervo are not trying to drill to extreme depths. Instead of going as deep as possible, they focus on creating more contact with the heat that's already there, where the heat is still useful, but the engineering is far more manageable.
And so what Fervo does is we'll drill down into rock that's 400 or 450 degrees Fahrenheit. And then rather than just leaving a simple vertical well that might only be a few inches in diameter, try to produce heat from that section, we'll turn and drill horizontally for over a mile.
That process increases the surface area that's exposed to heat, which means more energy can be captured. So then they pump water underground at extremely high pressure, cracking open the rock and creating a network of tiny fractures. And through those fractures, water can flow. It moves through the hot rock, heats up, and is pushed back to the surface. It's a process borrowed directly from fracking. Out in the Nevada desert, Google has already signed a deal with Fervo to help power its data centers.
You're going to be hooked right into the AI data centers soon, right?
Yeah, that's where all the new market is going in energy these days, is trying to figure out how do we power all this new development from AI and do so in a way that's sustainable and affordable. And geothermal has a huge role to play in that.
So Quaise has a goal of drilling the world's deepest hole, and they have a plan to get there. But some of the experts I spoke to remain skeptical.
People like Quaise have got a very, very steep road. I don't think that we're going to see a successful supercritical project in the near term.
Quaise is still 5 years away from commercial operations at their site in Oregon. And then there's the issue of whether or not using gas to return powdered rock to the surface is even viable after a certain depth.
What you see is that drilling on air can be a really effective way of getting down through some challenging formations that, frankly, mud-based systems struggle with. But there are limits because as you go deeper and deeper and deeper, it's harder to return that to the surface.
So the deepest holes that I've ever heard of that have been air drilled, which is the same, they're destroying the rock in a different way, but they're blowing it out of the hole as fine chips and dust, is about 10,000 feet. And that is pretty expensive to do.
Then there's the idea that any geothermal project using heat to generate electricity is incredibly inefficient.
As we take that working fluid and vaporize it and spin a turbine, a large amount of the energy that's present in that initial fluid escapes to the atmosphere, essentially as a required cooling stage that we have to do to make the power plant run. And only a relatively small amount of the initial energy is available in the final product, which is electricity on the grid. We're probably today with modern technology at about the 15% efficiency range.
So according to Wayne, the best use of geothermal is for direct heating and cooling.
If we're taking that geothermal energy and we're using it directly to warm something up, whether it's our living space or our dairy barn or our beer operation, we can dramatically improve the efficiency of the system. And instead of taking 15% of the energy, we could use something more like 85% of the energy.
That's what his team has done at Cornell University. Instead of traditional air conditioning, they use a passive system that's connected to Cayuga Lake,
where we allow heat to flow from campus to the cold, deep water of Cayuga Lake. And in doing so, completely bypass the efficiencies that are available with any other type of technology. So the cooling system that's in place today is probably 6 to 8 times more efficient than the world's second most efficient cooling system.
And finally, you don't actually need to go to 20 kilometers to access supercritical geothermal.
There's no reason from a point of view of having to produce usable heat to go to 20 kilometers anywhere on the face of the earth. It's too deep. From a science point of view, yeah, I could view it as, the analog to going to outer space. We're going to go to inner space and try to understand the earth better there, and we may discover some new things. But to claim that it's going to produce economic geothermal energy isn't necessary.
But maybe that's not the point. We're always going to wonder about the world beneath our feet. So how far can we actually go?
Oh, I don't think there's really any limit. We could go a lot deeper. It's just a question of what's the purpose and who's going to fund it. But it's definitely not a technological limitation.
I'm literally in the hole of a side of a cliff. Just another stupid thing I'm doing for a YouTube video. Look how deep that hole goes. With more people going to space than ever before, I wanted to know, are human beings ready to leave Earth behind? So, I talked to an astronaut who spent over a year up there.
Is it true that you're just wearing a diaper?
You know, it is what it is. If you outpace your diaper, it could just be a bad day.
I met with science writers.
This is my copy of your guys' book.
Nice.
Health experts.
As far as you know, has anybody ever had sex in space?
Love this question.
And a man who paid $30 million to join Russia's space program.
Where I would gladly volunteer for a one-way trip to live on Mars.
So what did I learn? Taking Homo sapiens multiplanetary isn't just hard, it's almost impossible.
Space can kill you rapidly or it can kill you slowly, but it's always trying to kill you.
And even if this migration to the stars takes centuries, the decades in between are gonna get weird.
ChatGPT, what would a real Mars colony look like?
You're probably going to have to drink recycled urine. Protein sources might be insects, which isn't for me. You might die of cancer. You'll probably be living underground. Your bones and your vision and your muscles might be degrading. Maybe you'll be okay, maybe not. And you're going to be living in a small, cramped habitat with people you may or may not like.
So how long can you actually last in space? Which dangers still stump even the scientists? And what if the hard part isn't the rockets and robots? It's us. The first limit of living in space is that we don't have that many places to go. Mercury's climate is both extremely hot and cold. The surface of Venus could melt lead, and the rest of the planets too far away. So the first idea is staying local in low Earth orbit. That's convenient, but it's getting crowded with thousands of satellites and space junk. Then there's the moon. It's not too far away and people have been there before, but it barely has an atmosphere, and nights last 2 Earth weeks. Then there's Mars, which has some of the stuff we need to support life, like frozen water. But what if building on something isn't the best idea? There's a whole group of engineers who think the future of humanity isn't on Mars or the moon. It's floating somewhere in between. That vision comes from a particle physicist named Gerard K. O'Neill. He imagined giant rotating habitats long before we even had Wi-Fi. I'll come back to him, but first I want you to meet some of his followers actually trying to make it happen.
Time to get into space mode.
I went to Houston, Texas.
New Worlds.
To an event called the New Worlds Conference.
Whoa. I want to get hit by
Yeah, now be careful with that.
Look at how janky this looks.
It's Space Expo meets Burning Man.
Here's a astronaut.
The event's founder, Rick Tumlinson, studied under O'Neill.
We used to call ourselves Jerry's kids. He was a true visionary. He was like, let's go out there and build space solar power plants, and these communities will be funded by building these and selling energy to the Earth. And then New Worlds is where we can start bringing the tribe together and inspire those people who are going to go.
Got it.
Right? And give them a home.
But by the way, you do have people coming to this event this time and probably in the past who are major space investors.
Absolutely. There'll be a couple of billionaires in the audience.
It's time for the Space Cowboy Ball Saturday night. I'm heading over there now. And y'all, I came prepared.
The event culminates with the Space Cowboy Ball.
Don't tell my wife or my rabbi that I was here.
It's part networking.
The best deals happen when you're at parties like this.
Part costume party.
Brock, tell us what your outfit is. I'm a space pirate.
As the people at the Space Ball partied like it's 2099.
Rocket Man!
I wandered through the empty exhibits at the Space Center Houston. From Skylab to 20-mile space stations.
Look, we got a guy taking a little shower break over there. Hi.
Stuff that used to feel like pure sci-fi, it's starting to look kind of doable. So how do we get from something as Spartan as Skylab to O'Neill's full-on space cities?
Good evening for Roundtable. I'm Harold Hayes. The most mind-boggling idea comes from the mind of a professor of physics named Gerard Kitchen O'Neill.
This is something which we feel could be made as a first model space colony for about the cost of the Apollo project.
O'Neill didn't just imagine floating cities. He detailed how to build them. starting with materials from the moon.
It's probably a rotten place to live, but as a mining source, it's great.
Lunar soil, called regolith, contains oxygen, aluminum, iron, and silica, and could theoretically be used to make fuel, glass, and solar panels. Rather than hauling heavy materials up from Earth, O'Neill invented something called a mass driver, an electromagnetic launcher that works like a railgun or magnetic roller coaster to fling raw material from the moon into orbit.
The bucket carries a payload of lunar material, and it's accelerated by these magnetic coils.
In orbit, those payloads would be caught and melted down in solar-powered furnaces to extract metals. This would feed a kind of orbital job shop, capable of manufacturing beams, solar cells, and eventually, more mass drivers. O'Neill's plan was a self-replicating industrial loop. One seed system could duplicate itself without needing anything new from Earth, and it could all be run remotely. The result would be giant habitats that rotate to generate artificial gravity, now known as O'Neill cylinders. Inside, lakes, farms, cities powered by constant sunlight, built from moon dust, populated by people, and possibly plants and animals brought from Earth. They'd orbit at stable points called Lagrange points, the perfect parking spots in space, just a few days from Earth. Once you know the shape, you start noticing O'Neill-inspired designs in lots of movies and TV shows. Here's Babylon 5.
Humans and aliens wrapped in 2,500,000 tons of spinning metal, all alone in the night.
And the craft seen in the movie Interstellar.
We're not meant to save the world. We're meant to leave it.
Ready-made space colonies, no long trips to Mars required. In his original notes, O'Neill admitted this vision might take centuries, but it remains one of the most compelling and fully thought out ideas for how humans could live long-term in space. O'Neill passed away in the 90s, but his legacy lives on. And one of his most famous students is closer than ever to bringing this dream into reality.
We can have 1 trillion humans in the solar system, which means we'd have 1,000 Mozarts and 1,000 Einsteins. This would be an incredible civilization.
Just imagine, prime one-day shipping for 1 trillion people. Jeff Bezos has been a space nerd since he was a teenager. Then, as an undergrad at Princeton, he attended seminars with O'Neill. So far, he's taken celebrities on suborbital rides with his company Blue Origin. But now, he's going for something much more ambitious. Landers on the moon, built to unlock its buried treasure. The scientific term for this quest is In Situ Resource Utilization, or ISRU. And if humans can't figure it out, the entire future of living in space could fall apart. Here's the problem. Even with reusable rockets, arguably the biggest advancement in space exploration in recent years, it's still really expensive to launch stuff off Earth. So if you want to build a base, or a civilization, you can't bring everything with you. You have to live off the land. That means taking dirt, ice, or atmospheric gases and transforming them into what you need: air, water, and fuel. Blue Origin has already isolated near pure silicon and other elements from simulated moon dirt in a lab. Next, they want to do it on the moon to extract materials for solar panels and maybe even manufacture them right there on the surface. Icon, a Texas-based construction company, plans to melt moon dust and then use robots to 3D print structures on the moon.
It's basically powdered sandpaper that we turn into a liquid sandpaper and put it through machinery.
Is it like 10,000 Wallies? Is it like one big robot? Like, what's the crew the robot crew that's going up there?
Great question. I would say it's close to 10 to 15 robots would be just a wonderful fleet to go after a couple of pretty big ambitious plans. So things like landing pads, roads, protective structures, some of the early infrastructure that we want. And that would provide the redundancy, but also the fit to function.
Other groups are focused on pulling oxygen and hydrogen from lunar ice to make breathable air, drinking water, and rocket propellant. If that works, you don't have to ship fuel from Earth anymore. You just gas up on the moon. Sounds simple, right? Well, it's not. Just ask Kelly and Zach Weinersmith. They wrote an entire book about what makes space so hard.
So there is technically water in the regolith, but you could also technically say that about concrete. So we did a back of the envelope calculation, and you would need to bake about 6 tons of lunar regolith to get enough water to have like the 3 kilograms that you would need for things like drinking every day. And that doesn't even include the water you would need for things like showering or water balloon fights.
There are higher concentrations of water ice at the moon's south pole, in the bottom of craters that never receive sunlight. But turning any of that water into fuel using electrolysis requires a ton of power.
When you're making the propellant to go to Mars on the moon, that's when you need the megawatt or so.
And the moon only gets sunlight for half the month, which makes getting all your energy from solar a challenge.
And so that's why we're a big fan of nuclear fission power for the moon, to be able to make enough power to do propellant production at scale.
And finally, you have to build all of this on the moon. Outside the lab, the only space mission to do ISRU was the Mars Perseverance rover. It produced about 120 grams of oxygen from the Martian atmosphere in 2023. That's about as much oxygen as a human breathes in about 4 hours. And while this sounds like science fiction, a survey shows that commercial space insiders are gung-ho on the technology, estimating that ISRU could be operational and commercial by 2040. Elon Musk, on the other hand, is looking for volunteers to build a city on Mars for 1 million people.
You may not come back alive, but it's a glorious adventure.
Also, a very expensive one. Musk's plan hinges on Starship, the biggest, most powerful rocket ever built. The idea? Launch Starship into orbit, send 5 to 8 tanker ships to refuel it, then fly to Mars.
If we achieve orbital refilling in time, then we will launch the first uncrewed Starship to Mars at the end of next year.
Aside from the fact that it will be the longest manned space mission of all time just to get there, the first challenge is landing. Mars descent is one of the hardest problems in aerospace engineering. NASA's blunt about it. The system that landed Perseverance does not scale to human-class elements. It's like dropping a Winnebago from orbit into a windstorm and hoping the airbags work. And if you crash, you don't just lose cargo, you lose the crew. And even if they stick the landing, the entire return trip depends on ISRU. The SpaceX plan is to mine water ice for hydrogen and suck CO2 from the thin Martian air. Then run it all through a Sabatier reactor, an industrial device that turns it into water, oxygen, and methane. That's rocket fuel, baby. SpaceX calls this plan refillable Mars, but critics say it's more like regrettable Mars. Aerospace enthusiast Miguel Gurrea says the SpaceX mission gambles everything on a single point of failure.
It's a bit fragile in that if it fails and you don't have a backup, astronauts can be stranded there.
If the Sabatier reactor breaks, if the Martian ice is buried too deep, if dust storms disable the solar panels, you're maybe forever. And remember, there's no second ship, no alternate ride home, just one crew, one plan, one shot. The biggest challenge? Power. A Mars-to-Earth return using SpaceX's Starship would require a massive ISRU infrastructure, consuming 3.37 megawatts of continuous power and producing 2,400 tons of propellant for 2 returning Starships. That's enough to power about 1,500 American homes. It's equivalent to a solar farm the size of 20 football fields, delivered to Mars, fully operational, and able to run 24/7 for over a year. But Mars is dusty, very dusty. Dust storms can last weeks and even months, and they happen about 40 to 50% of the time during a standard 2-year Mars mission. That means your solar array could get buried, just when you need it most. Gurrea's alternative? Send smaller missions. Pre-deploy the fuel, use multiple vehicles, and build in backups. It's not flashy, but it's safer. And even if you survive, the final boss awaits. Launching off Mars. We've never done it before, not even with robots. NASA's current concept for a Mars ascent vehicle would require over 25 tons of fuel to get 4 people back into orbit. Whether it's Bezos building moon factories or Musk betting it all on Martian methane, ISRU is the linchpin of the two most prominent off-world plans. Until these companies prove they can mine ice, generate megawatts of power, and build chemical plants on alien worlds, the dream of living in space is just one broken Sabatier reactor away from becoming a very expensive camping trip. And with odds like that, who's actually going to take the 2 to 3 year trip to Mars? Only someone who spends most of their adult life preparing for it. March 1995. Arkalyk, Kazakhstan. Cosmonaut Valery Polyakov has just landed after 437 consecutive days in orbit, the longest spaceflight in human history. As he stumbles out of the capsule, he reportedly says, "We can go to Mars."
And that really showed that there were no fundamental deal breakers to staying in orbit for years at a time.
Jonathan McDowell would know. He spent the last 50 years documenting every single object and person who's ever left Earth.
I'm the chronicler of the space age. I try and be the journal of record for what actually happened in outer space.
He's currently got 200 bookcases and counting, roughly 1,500 square feet of binders filled with space history. And yes, he's still workshopping the name.
One of the places I might end up is Bromley in London, and so it might be the Bromley Astronautics Research Facility, or BARF.
On Jonathan's master list, Polyakov is astronaut number 214. Katy Perry?
I'm going to tell you something right now. You are officially an astronaut.
Thank you so much.
I believe I have her as astronaut number, or space traveler number 729.
That's it. Only 750 people ever have crossed 80 kilometers into space, according to Jonathan's records.
The older people will be blown away by how many it is, and younger people will be surprised by how few it is.
The American with the record for the longest stint in space? NASA astronaut Frank Rubio.
What do you think? It's amazing. Oh, man.
Who spent 371 days aboard the ISS.
It took about 6 months to get back to 100%. But about 2 months, I was, for all intents and purposes, to any outsider, they would have said that I was back to 100%.
Getting to space takes more than a dream. It takes a resume built like Tony Stark's LinkedIn.
I always like to say we look for adventurous nerds or nerdy adventurers, right? And so you kind of have to have both types of things where you love to learn.
At minimum, you'll need a master's degree, technical or military expertise, Russian language skills, survival training, and years of physical and psychological prep.
You think of the billions and billions of people who've ever lived. That's just a small number. And so we just don't have enough data to generalize, hey, how is it going to affect humanity as a whole versus these individuals?
Altogether, you're looking at 10 to 15 years of work before your first space mission. If you ever get to travel, that is.
Even though you can look down and see the planet, it's just this weird dynamic where you have a view like no other, but you're stuck in this little itty bitty space.
The ship has cleared the tower.
And New Shepard has cleared the tower on our way to space with our first human crew.
But not everyone goes through NASA. If you've got deep enough pockets, you can just buy your way to space. No one knows exactly what Katy Perry paid Blue Origin, but the deposit alone is $150,000. And the full price ticket can cost millions.
That's amazing.
If that's too steep,
Mach 1, pilots are now trimming nose up.
Virgin Galactic offers a shorter hop to the edge of space for about $600,000.
I was once a child with a dream, looking up to the stars. Now I'm an adult in a spaceship.
Which brings us to one of the wildest space tourists of all. Meet Nick Halleck, certified cosmonaut, millionaire investor, rock musician, and lifelong thrill seeker.
This shaft goes all the way down to the blast doors.
He's also the proud owner of a large decommissioned nuclear missile silo.
Like it's your own little Universal Studios here. It's like this is your dystopian Disneyland, So welcome to the abode. Welcome to the complex. Like private residence here.
One he's turning into a disaster-proof commercial hub, complete with a firing range, diesel tanks, a Faraday cage, and eventually its own nuclear microreactor.
This can withstand a direct nuclear strike, and it is EMP proof.
To Nick, it's not a doomsday bunker, it's an insurance policy.
Well, I'm not a doomsday prepper, I'm an entrepreneur. I think what you're going to find is a lot of individuals culminating together with like-minded folk to ride out any turbulence or any storm out there in the marketplace. And I think that's where we are right now.
Nick has spent tens of millions of dollars buying rare historic real estate. He's invested in castles, lighthouses, farmland, and now Cold War-era bunkers. Russia assigned Nick to 2 space missions as a backup crew member. He hasn't been in orbit yet, but he says he's ready to leave Earth for good.
My goal is to walk on the moon, but there will come a time where I would gladly volunteer for a one-way trip to live on Mars and colonize and terraform Mars. And those going to Mars, you'll have to understand it's a one-way trip.
For people like Nick, space is within reach because they can afford it.
Do you think that space is only destined to be like a billionaire's playground, or do you think like the average Joe might also
I think
have
it'll
to
be billionaires and like 9-figure multi-millionaires, and eventually it'll come down as the passage to space becomes far more inexpensive.
But let's be real, most of us are never going, not unless something changes dramatically.
That's amazing.
And even the elite few who do go still face a universe that's filled with an invisible force that can slow roast you alive. Floating around Earth are 2 invisible donut-shaped rings of charged particles. They're called the Van Allen belts, a benefit of Earth's active molten core. These belts trap harmful solar and cosmic radiation, acting as part of a larger shield that protects everything below. But the further away from Earth you go, the weaker that protection becomes, and radiation levels rise fast.
I think radiation is probably the biggest concern. Once we get outside of the Van Allen belt, that risk exponentially grows.
And what happens when we do? Cancer, cataracts, heart problems, brain damage, down the pike genetic mutations. Just your standard doggy bag from the Galactic Barbecue.
We've now added a new one, and that is cognitive decline from neurotoxicity, basically, from radiation.
Dr. James Logan was a medical advisor and mission control for 25 NASA missions. But he says his former agency isn't taking this threat seriously.
And it's funny, but NASA really doesn't seem to care about radiation. And the reason is you can almost compare NASA to the NFL and radiation to CTE, chronic traumatic encephalopathy. What NASA's concerned about is the mission. What a football coach is concerned about is winning the game. But CTE is bad chronically later on for a football player, and radiation can be terrible for an astronaut later on in their lives.
Astronauts aboard the ISS are exposed to radiation levels 100 times stronger than Earth's surface. To reduce astronauts' risk of cancer, NASA limits crew members' total career radiation dose to 600 millisieverts. For comparison, the average American living to 70 years old is exposed to around 430 millisieverts over their entire lifetime. But step outside Earth's magnetic bubble, that number jumps fast. Take a 3-year mission to Mars, and you could be exposed to 1,650 millisieverts. That's the equivalent of over 16,000 chest x-rays.
The sun is always blasting out hot ions, which is not great if you're in space, but now and then it shoots a sort of flashlight of doom in one direction in what's called a solar particle event, which is an event in the same way that a tsunami is a water event. And the good news is that space is big, so if the sun is shooting out beams of doom, you're probably not in them. But if you are, essentially the risk is you get acute radiation sickness, which is essentially the worst way to die.
A direct hit from a solar flare could expose astronauts to 2,000 millisieverts and cause radiation sickness within hours. In 1972, one such flare erupted between Apollo missions. If it had struck while astronauts were on the moon, it likely would have killed them in hours. Dr. Logan says radiation protection should change how spacecraft are designed.
So you basically build the spacecraft around the crew. So instead of long, pencil-thin rocket ships for interplanetary flight, they would be short, stubby, spherical spacecraft in which the crew is right in the center. So they're surrounded by as much mass as you can get, and that would enhance their radiation protection.
So this? Yeah, not exactly realistic.
If human beings ever live or work on the moon or Mars, they're going to have to live like ants, earthworms, or moles, because otherwise the environment just won't tolerate it.
That means no strolls under the stars, more like digging in and staying there. Some scientists think ancient lava tubes, natural tunnels carved by molten rock, could be our best hope. Buried beneath meters of rock, they could provide natural radiation shielding for long-term habitats. Others have suggested piling rocks into a mound before the humans arrive.
We don't know where the caves are, we don't know if there's many caves, if they're reachable or not. So what we're doing is recreating our own cave, our own shell structure under which these astronauts would be living. So it's made with local material, local regolith or Mars dust to protect our astronauts from that. So that's kind of a really big design driver for a base like that.
We came up with some walls that were about somewhere around a meter thick. And we did something I thought was pretty clever at the time. You can see this sort of waffle cone structure here, and we can fill that with compressed regolith that we don't process.
Whether we end up burrowing into lava tubes or piling up space rocks, one thing's clear. Even if we manage to survive all that space radiation, we've still got another pesky problem. Our squishy human bodies need calories, constantly. The first human meal in space, 2 tubes of meat puree and 1 of chocolate sauce. Yuri Gagarin slurped them down during his 108-minute flight in 1961, and in doing so, proved that you can eat upside down at 17,000 miles per hour. Since then, space cuisine has come a long way. Out with the squeeze tubes, in with the thermo-stabilized entrees.
Meat and vegetable Russian stew, roasted quail, oatmeal with brown sugar, but look at how it's packaged. Real astronaut food. What's this? Mac and cheese, anybody?
You might notice there's all sorts of foods here. It's like opening the refrigerator.
Today's astronauts rotate through menus curated by food scientists, designed to be balanced, shelf-safe, and ideally edible. Frank Rubio told us one of the biggest surprises.
All the food in general was pretty good. I love seafood, and so I had them fly me a bunch of canned seafood. And so anytime, and for most people, like a can of sardines doesn't sound great, but for some reason up there for me, any sort of canned seafood, anytime I would open it, whether it was mackerel or sardines or tuna, it was great.
But that's feeding a crew of 6 in low Earth orbit, with regular supply runs from Houston. Try doing that for 1 million people, 34 million miles away. That's the real challenge. Most sci-fi movies show gleaming greenhouses on Mars, lush with crops and tended by astronauts in cool visors. In reality, the dirt alone is trying to kill you. It's called regolith. The loose, jagged rock and dust covering the moon and Mars is nothing like Earth soil. Breathe it in enough times and it scars your lungs. You could die just from that. Even NASA's tech isn't immune. In 2009, the Spirit rover got stuck in Martian soil so badly that engineers on Earth built a full-scale replica of the terrain just to figure out how to free it. They never did. Spirit is still there, buried alive by Martian dust. And even if you could grow food in Martian soil, you probably shouldn't. It's full of perchlorates, toxic compounds that interfere with thyroid function and would need to be filtered out before you could safely grow anything. Martian soil has just a 1% concentration of perchlorates, but that's 400,000 times too toxic for humans. So how would we actually feed people?
If you want to get protein from animals, you might be getting it from insects. The idea was you can grow plants, and the part of the plants that you don't eat, or that humans don't eat, can get fed to the mealworms, and now you turn food waste into protein.
Lentils and bugs. It's not exactly the interstellar farm fantasy. And if you're thirsty, keep in mind, water is scarce, which means you'll likely be drinking, well, yourself. On the International Space Station, water is recovered from everything. Urine, sweat, exhaled breath, you name it. NASA's system recycles about 98% of all water on the ISS. In space, every drop counts. even the ones you've already had. And what goes in must come out.
In case you ever wondered what a space toilet looks like, here it is.
Early space travelers used plastic bags. Skylab had a slightly upgraded system involving suction and leg restraints.
Time to go.
Today's astronauts use more advanced toilets.
And you carry on. You hear the fan noise. Check for airflow. That's where your business goes.
But the core challenge remains, dealing with human waste in zero gravity.
Okay, so what's a brown trout? Okay, what's a brown trout? A brown trout is one of the many euphemisms astronauts have developed for floating fecal waste, which is a common feature of outer space. I believe that coinage is from the space shuttle program, but there were others. Escapees was a nice one. And, maybe worth noting, this is, maybe one of the funnier things in space. It's also incredibly dangerous.
But on spacewalks, there's only one way to handle your business.
I hadn't used a diaper in 40 plus years, right? Usually around 1 year old, most of us stop. And things that you don't think about is essentially you have to meter your urine flow, right? Because because of the lack of gravitational force. And so if you let go of your full bladder worth of urine, it's going to overwhelm the diaper and essentially form a blob of floating urine inside your spacesuit. Because if you outpace your diaper, it could just be a bad day.
And on Mars, waste becomes even more valuable. Not just something to get rid of, but something to reuse. Poop, sweat, breath, all of it gets cycled back into the system. There have even been experiments to grow vegetables using human hair and nails. And before you think this all sounds a little extreme, just remember, we've tried to build a self-sustaining ecosystem on Earth once. It was called Biosphere 2, a $200 million dome in the Arizona desert, designed to house 8 people, grow all their food, recycle their air and water, and prove humans could survive in a completely sealed environment. They had sunlight, gravity, Earth air right outside the walls, and still, it barely worked. Oxygen levels dropped. Crops struggled. The team split into factions. They made it 2 years, but barely. And now the plan is to do that again, on a dead planet with dirt that's poisonous. So yes, the future of space settlement may involve sustainable farms, closed-loop water systems, and eco-friendly Martian composting. But right now, we're still figuring out how to deal with poop. And even if we manage to feed and hydrate a colony millions of miles away, there's still one big problem. What happens when someone gets sick? In 2023, an ER physician named Nathan Jones spent 378 days sealed inside a 3D printed habitat in Houston, alongside 3 other volunteers. The goal? To find out what it would be like to live and work on Mars.
The minute that we were in and they closed the door, it was like, man, did I just do that?
NASA called it the CHAPEA mission, short for Crew Health and Performance Exploration Analog. Analog astronauts are people who simulate space missions without leaving Earth. CHAPEA was NASA's longest analog to date, but it's only about a third the length of a crewed mission to Mars. For a full year, the team lived in isolation inside a hangar, ate shelf-stable plant-based meals, and even suited up to explore a simulated Martian surface. No escape, no sunlight, no shortcuts.
I felt like our mission was a success and that we kind of proved that the isolation was something that humans can overcome with the right tools.
Astronaut Frank Rubio agrees.
We're getting pretty good at the psychological parts of it. A lot of that's just picking the right people, the right personalities.
Okay, so maybe the mental toll of space isn't as scary as we feared. I mean, we all survived COVID lockdowns. Kind of. But on Earth, healthcare is a 911 call away. On Mars, you could be 200 million miles from the nearest hospital.
That's the closest hospital. You've got to really be able to think under that pressure.
Now imagine someone needs surgery in microgravity.
If you make an incision in the skin, you're going to hit some blood vessels, some small ones or maybe some venous blood vessels. Hopefully you don't hit an arterial vessel. And what's going to happen is blood isn't going to come out and just roll down through the force of gravity. It's going to pool at the wound.
So yes, surgery is possible in simulated zero-G, but it's also risky, equipment heavy, and prone to failure. Infection control? Questionable. Anesthesia? A whole other challenge. You can't use gas-based painkillers in a sealed cabin. One leak could contaminate the air.
So you'd have to worry about everyone getting anesthetized. But, you could be pretty careful about that. Another option is to sort of inject into the spinal cord, but fluids tend to shift upwards in space, and so you might have problems where the anesthesia doesn't get distributed as well as you would like it to.
Back in the 1990s, NASA ran surgical tests aboard a parabolic aircraft that simulates microgravity, nicknamed the Vomit Comet. In one test, a surgeon opened an artery in a rabbit and watched the blood form floating globes. Later, they successfully performed laparoscopy on a 100-pound pig.
So the answer to when will we understand this problem better is when pigs fly.
Another issue with medical equipment, it takes up a lot of space.
As you can imagine, Mars or lunar habitat are going to be pretty space limited, and so it's going to be important to find ways to work in a space that you hopefully never need.
That's why researchers are turning to on-demand fabrication, like 3D printed splints, customized to the astronaut's body.
Whoa. No worries. Sorry. No problem. It didn't break. All good.
This is the kind of research that happens at TRISH, the Translational Research Institute for Space Health. It's a NASA-funded consortium based in Houston. TRISH collects biomedical data from commercial space flights, and it's building a database to help understand what happens to the human body in orbit and beyond.
We work with NASA on the same risks, but we are trying to understand this for all of humanity. So at some point, as our race or species further and further starts going into space, more and more of us go into space, we got to understand how the body changes in spaceflight.
TRISH is also working on real-time solutions, like treatments for space motion sickness, which doesn't act quite like seasickness or car sickness.
The symptoms are exactly the same, but like I said, we were unable to predict it. Heel to toe, let's do 10 steps, 2, 3.
Astronauts undergo pre- and post-flight testing, including obstacle courses to measure balance and coordination.
And splashdown, Crew 9 back on Earth.
As returning astronauts know, gravity is virtually non-existent in free space, and on other worlds, it's wildly different. If you weigh 150 pounds on Earth, you'd weigh just 57 pounds on Mars and only 25 pounds on the Moon.
My weight on the Moon, 62.2 pounds.
Astronauts adjust surprisingly quickly to moving around in low gravity.
After about 8 months, you genuinely almost, not that you forget how to walk, but you forget what it feels like to walk, and floating just becomes your perfectly normal feeling day-to-day kind of moving yourself around. And so I think one of the things that surprised me the most is how adaptable our brain is.
But while your brain adjusts, your body doesn't. In microgravity, your bodily fluids shift upward.
And for the first couple of weeks, you feel really stuffy and just kind of like you have a head cold. And that's just due to all that extra volume in your head. And so your heart, for every stroke that it pumps, it now has a significantly greater volume. So the stroke volume is increased, and that puts a lot of stress on your heart.
But perhaps the biggest challenge in zero-G is bone loss. Without gravity constantly pulling on your skeleton, your bones start to deteriorate fast. It hits the weight-bearing bones first, your spine, hips, and legs. That's why treadmills and resistance machines are essential in orbit. One of the most important, ARED, the Advanced Resistive Exercise Device.
ARED uses 2 vacuum cylinders to recreate that resistance, an hour of intense work in to replicate the 24 hours worth of pressure that your bones would otherwise be feeling.
Some scientists say the answer to all this is simple. Just spin the spacecraft. Rotating a habitat can simulate gravity through centrifugal force, like in the O'Neill cylinders. But there's a catch, and the Wienersmiths call it the washing machine effect.
Which is that if you have ever had a washing machine and all the towels were on one side when it started spinning, it didn't just spin nicely, it started wobbling, right? Now, in your washing machine, that's a slight concern. In a rigid outer space structure, that's a terrifying concern. And so you try to imagine you've got a rotating space station, and then there's a Taylor Swift concert on one side. So everybody goes, right? Now you've created the washing machine problem. I depending on where the crack goes, maybe all of Taylor's audience gets sucked out into the void.
So, do we bounce back after a stint in zero-G? NASA's landmark twin study helped answer that. Astronaut Scott Kelly spent nearly a year in space. His identical twin, Mark, stayed on Earth. When Scott returned, researchers compared everything, right down to the DNA. Many of Scott's physiological changes reversed after he came home, but some didn't. He came back with DNA damage from radiation, increased inflammation, slower cognitive processing, dizziness, and nausea on re-entry. And here's the catch. We've only studied zero gravity and Earth gravity. We know almost nothing about what happens in between. How does the body respond to living on Mars gravity or moon gravity for years?
What we don't know, after 63 years of human spaceflight, we do not know the gravity prescription. We don't know the dose, we don't know the frequency, and we don't know the side effects. And there will be side effects. We just don't know them yet.
Right now, it's an open question with no good answers. NASA has tried countermeasures, including one particularly strange solution: sucky pants.
So the idea here is that you get into these pants, or in some cases it's a sleeping bag, and it creates lower pressure around the bottom of you, which results in the fluids up higher shifting down in response to that change of pressure. But sometimes it happens too fast, and there have been stories about cosmonauts sort of passing out as the fluids go down into the sucky pants. And I've seen pictures of the sucky sleeping bag, and it doesn't look very comfortable.
Turns out zero gravity makes it hard to stand, sleep, and snuggle. In the 1980s, engineer G. Harry Stine made a shocking claim.
Sources inside NASA have informed him that there is work on in neutral buoyancy tanks having space sex. And so what do dolphins have to do with this? Well, there's a claim that what dolphins do is have what you might call scientifically obligate threesomes, in which, in order for two to clasp each other, there has to be a third wheel, a third flipper, I don't know, to make sure everyone's going in the right.
Yeah. Hold them in place.
Yeah. And so there's just, let's say, some problems with this idea, one of which is dolphins don't. And so
they manage this feat just fine in the water by themselves.
They're not the one, maybe there's some organism that actually does this, but it seems like evolution might have been, I don't know, having a late night, I don't know. Yeah. But what we figure is either someone at NASA or just someone was having a laugh with Stine, and Stine just bought it. Like, they apparently sent him a document with their logo, like they had a club. And then anyway, so the point is the Three Dolphins Club is supposedly assigned to anyone who had actually accomplished it in space. And which supposedly happened repeatedly on the shuttle. Again, according to Stine and no one else. We are skeptical.
Every step of human reproduction, implantation, fetal development, delivery, evolved on Earth. In space, we're in the dark. As far as you know, has anybody ever had sex in space?
Love this question. So there are, looking at it, I do not believe personally that intercourse has ever happened in space. To answer that question, self-activity has. Can I say the word masturbation on here? Self-activity has certainly occurred in space.
Alex Leyendecker is the founder and director of the Advanced Space Life Research Institute.
We're a 501c3 nonprofit research organization based in Cape Canaveral, studying the space life sciences, but a lot more specifically, human sexuality and reproduction factors as they apply to outer space.
So far, science has never seen a successful mammalian pregnancy in space. Not in humans, not even in mice.
It was 5 female rats and 2 male rats into orbit, and those rats copulated, but no pregnancies resulted.
Not a great look for the million astronaut Musk plan.
I guess our view is, if you do as some very rich people are advocating and send 1 million people to Mars at once, they are going to try to have children. And we consider that essentially unethical. It'd be kind of like having babies in the middle of Chernobyl just to see how it goes. It is possible it's going to be fine. People in the early spacefaring days thought maybe it would be impossible to eat in space, and it just turned out you can. So we'd like to get those data first, though, before we start sending children to this environment. And so the best way to do that would probably be to gradually ramp up invertebrates on the moon.
Alex's ASRI organization has designed future rodent experiments, but human experiments could be a long way off.
As we have it projected right now, we're looking at hopefully being able to have the first full-scale human conception, development, and live birth and delivery in space by 2055.
But private space stations are coming soon. Civilians are already flying, and eventually, someone is going to try.
They're going to go up there and try and do the deed, and we don't know the outcome yet. We don't know how it's going to work.
For sure.
Without human reproduction, there is no future in space. No colonies, no cities, no second generation. We can launch billionaires. We can build bunkers on the moon. But if we can't make more humans, then space isn't a new frontier. It's just a very expensive hotel with no checkout policy. We've talked about fuel, food, gravity, radiation, and reproduction. But there's one more thing space explorers will have to figure out: rules.
So, according to the 1967 Outer Space Treaty through the United Nations, no individual or nation or company is supposed to go out and claim sovereignty over anything in space. But Elon Musk, in the Starlink Terms of Service, says that they're going to go out and start a nation on Mars, and that the people on Mars will not be beholden to the laws of Earth. And so what concerns me is that the person who has the most money and the highest probability of actually starting settlements in space clearly plans to disregard international law.
If a billionaire builds a habitat, hires a crew, and something goes wrong, whose court do you go to? There's no precedent, no sheriff, no enforcement agency. Space governance might sound boring until it isn't. Because when things go wrong in a sealed metal tube 34 million miles from Earth, you better know who's in charge. It's easy to get swept up in the fantasy of cities on Mars, space cowboy balls, and trillion-person solar civilizations. But the truth is, we've barely figured out the plumbing. So how long can humans survive in space? Probably years at a time. At least long enough to make it to Mars and back. But even if that's true, it's fair to ask, why leave Earth at all? A 2023 Pew survey found that only a small fraction of Americans think sending astronauts to the moon or Mars should be a top NASA priority. Far more say NASA should focus on things closer to home, like climate change and asteroid defense.
Can we, as humanity, live on Mars? I think with the mindset that we have, or the knowledge set that we have today, the answer would be no. But I think if you had asked any of us 20 years ago about certain technologies that we have now, right? Like, hey, are we ever going to have rockets that are landing their first stage back on Earth, right? Are we ever going to have humans that are living in space for more than a year? Heck, are we ever going to have all the capacity that a cell phone has, right? All of us would probably said no 20 years ago. So I think only time and creativity and engineering are the things that are not limited. So I think we can resolve any of those problems. It's just going to be a little bit of time and creativity, and we'll get there.
Right now, civilization is not ready to expand to the stars. Not technically, not biologically, not politically. But that doesn't mean we won't try.
If we continue on the same trajectory right now, we probably have another 90 to about 120 years of existence on this planet before we may become endangered.
Because space has always been a mirror, reflecting not just our technology, but our fears, our ambition, and our imagination.
We're all standing on the edge of this possibility.
Yeah.
And out there is this undiscovered country called the future. It's called the galaxy. It's called the universe.
Okay.
It's called hope.
Okay.
We need hope, man.
And in space, even the skeptics in the end think that our only future will be among the stars.
I have to admit I'm kind of a true believer when it comes to permanent human expansion in the solar system. I think it's real clear. We either leave the planet or perish. It's just that simple. And the universe doesn't seem to have a stake in the matter at all. It's almost like, we can do that and survive, or we can not do that and eventually perish. It is true, single planet species don't survive.
To be honest, to the extent people see our book as a kind of like, let's never do this manifesto, we regret it. I mean, I don't think we say that anywhere. We're mostly pushing back against silly ideas, or the idea that we can do this immediately, or that it would be ethical to do it immediately. For us, doing it right means handling all these difficult medical problems, especially reproduction, handling the need to be able to create artificial ecologies on other planets that can sustain people safely, and then somehow finding a way to make a legal structure that allows all of this to be at least moderately harmonious so that we don't increase the danger to ourselves by expanding outward.